Rajput sir, good
Hello,
morning.
morning, good morning. Am I audible?
You're audible but not visible.
Okay.
Monitor. Sir, shall we start with your due permission, sir?
Good morning, Dr. Rajput.
I'm trying. Am I visible now?
No,
What should I do?
if you log out and log in again, I think it might happen.
Sir, I think some problem in his camera. Its black screen is coming only. Some problem in his camera, black screen is coming.
Hello? हेलो
Yeah, Dr. Rajput, you are not visible.
मैं कैमरा अपना ऑन तो कर रहा हूँ, इसमें दिक्कत क्या आ रही पता नहीं चल रहा मुझे. व्हाट इज
तो कोई
प्रॉब्लम?
बात नहीं, नहीं तो बिना कैमरे के भी आपकी आवाज आ रही है हमारी तक. आपको हम लोग दिख रहे हैं पूरे.
विजिबल नहीं हो?
अभी
कैन
नहीं
यू
हो
सी
रहे
अस
सर, अभी
नाउ?
नहीं हो रहे. आप सर एक बार लॉग आउट करके लॉग इन कर लीजिए, शायद कुछ गड़बड़ होगी. शुरू में ऑफ हो गया वो कैमरा, हो सकता है.
कैमरा ऑफ क्यों हो रहा है?
एक बार आप सर लॉग आउट कर लीजिए, फिर लॉग इन कर लीजिए.
ऑफ करके लोड करता हूँ, ठीक है.
लॉग आउट देन लॉग इन, यस अगेन.
डॉक्टर राजपूत, आप मोबाइल से भी लॉग इन करके देख सकते हैं, शायद उसमें आ जाए तो.
ओके. हेलो हेलो।
Yes, sir.
यू ऑडिबल सर?
लेकिन कैमरा कैमरा अलाउ नहीं कर रहा है ये।
चलिए सर, कोई बात नहीं, अपन शुरू करते हैं। आई थिंक वी कैन गो एट, ऑलरेडी लेट।
ओके, अनेबल टू
आप
एक्सेस
प्लीज
कैमरा।
आप स्टार्ट कर दीजिए, आपकी आवाज तो आ ही रही है।
ठीक है, ओके ओके।
या
मैं
तो
देख रहा हूँ आप लोगों
डॉक्टर पंकज, यू कैन स्टार्ट प्लीज।
Yes, sir. Dr. Ashish, please.
को।
Thank you, sir. A very warm and pleasant morning to all the distinguished guests, dignitaries, faculties, and students present here today. I, Dr. Ashish Singh Parita, accord a warm and cordial welcome to all to the inaugural session of the National Workshop on Advanced Characterization Tools and Techniques for Material Science and Engineering, organized by Department of Physics, Amity School of Engineering and Technology, Amity University, Madhya Pradesh. It is our proud privilege and honor to have with us the distinguished guest, Professor Dr. B.S. Rajput, ex-Vice Chancellor, Kumayu University, Nainital, Honorable Pro-Chancellor, Lieutenant General V.K. Sharma, Sir, Ati Visastra Seva Medal, Honorable Vice Chancellor, Professor Dr. R.S. Tomar, Sir, Honorable Pro-Vice Chancellor Research, Professor Dr. M.P. Kaushik, Sir, Directors and HOIs, all faculty members, participants, attendees, and the students in the online mode. I once again welcome all respected guests and thank you all for sparing your valuable time to be with us today. To mark the beginning of the workshop, let us take the blessing of the Ma Saraswati, Goddess of Knowledge, and fold our hand for the prayer.
या कुन्देन्दुतुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा।
Thank you, everyone. Before we move ahead, we would like to take a moment to facilitate our esteemed guest. Even though we are meeting in a virtual mode, our respect and gratitude remain the same. We request everyone to join us in extending a warm virtual felicitation to our honored guest, Professor Dr. B.S. Rajput, Sir, Honorable Pro-Chancellor, Sir, Honorable Vice Chancellor, Sir, Honorable Pro-Vice Chancellor Research. I respectfully invite our Honorable Pro-Chancellor, Lieutenant General V.K. Sharma, Sir, virtually welcome Professor Dr. R.S. Rajput, Sir. Thank you, respected dignitary, for gracing the event. Now to give us an overview of the national workshop and its objective, I invite Professor Dr. Pankaj Kumar Mishra, HOD Physics and Secretary, to introduce the national workshop on advanced characterization tools and techniques for material science engineering. Please, sir.
Thank you very much, Dr. Ashish. Very good morning to our chief guest, Professor Dr. B.S. Rajput, ex-Vice Chancellor, Kumayu University, Nainital, Honorable Pro-Chancellor, Sir, Honorable Vice Chancellor, Sir, Honorable Pro-Vice Chancellor Research, HOI, HODs, dear scholars, respected speakers, and dear participants. It is my privilege as a head of Department of Physics. I welcome you all in this additional workshop on advanced characterization tools and techniques for material science and engineering. In the present era of rapid technological advancement, we are working on the scientific research and materials are still in infancy stage in India. This understanding becomes possible through research advancement, through characterization in the domain of electronics, nanotechnology, mechanical engineering, biotechnology, aerospace, renewable energy, and numerous engineering domains. So this understanding become possible in the today's workshop is the comprehensive platform to explore state-of-art characterization method such as X-ray diffraction, scanning electron microscopy, transmission electron microscopy, atomic force microscopy, Raman spectroscopy, FTIA or UV, electrical and magnetic property. So this particular topic is very vital and based on the application of these techniques in the wide spectrum of scientific and engineering research. So the reverse engineering is taking place in the different area. So this particular workshop encompasses the basic find. So the research on nanomaterial, they help us to determine size, shape, crystallinity, and functional behavior of sensing and the catalyst medicine. In electronics and semiconductor engineering, XRD, TEM, and Hall effect measurement just provide the particular glance in this scenario. In the engineering, it just try to take the characterization with the help of basic determination so that in terms of battery and the solar fuse, we can compass. In mechanical and material engineering, the same XRD and the particular part we just try to encompass in the help of the analysis and metal compounds. In chemical and polymer engineering and intermediate research, that is the backbone in terms of biotechnology, environmental engineering, and nanomaterials and smart material. So by bridging research excellence and engineering application, today's workshop aims to inspire new collaborations, foster practical understanding, and strengthen the scientific ecosystem. As materials becomes more complex, multifunctional, and advanced characterization will continue to drive discovery, product development, and industry innovation. I sincerely hope that workshop, lecture, demonstration, and discussion will enrich your understanding and knowledge. So with this, once again, I welcome each of you and wish a particular workshop. Thank you very much.
Moving forward, before inviting our Honorable Vice Chancellor, Professor Dr. R.S. Tomar sir, to deliver the opening remark, allow me to present a brief introduction of his esteemed profile. Professor Dr. R.S. Tomar is MSc, MPhil, PhD, FRSB London, FCBWS Hong Kong, FICER, FSLSC, FIASC, is the Vice Chancellor of the Amity University Gwalior. He has served the Vice Chancellor of IAS University Bhopal also. He was the founding campus head of the Amity Gwalior campus. He was the director and head of the Amity Institute of Biotechnology, Dean Life Science, and Dean Academics of Amity University Madhya Pradesh Gwalior. Professor Tomar has more than 33 years of teaching, research, and administrative experience in higher education in varied disciplines of science, including life science. Professor Tomar is actively engaged in teaching, research, and innovation. His research interests include nanotechnology, microbiology, herbal medicine, cancer biology, animal biotechnology, and environmental biotechnology. He has to his credit more than 150 research publications published in various national and international journals of repute. He has filed 27 patents, of which 26 has been published in Patents of Journal of India. 2 patents have been granted and other 1 are under the process for grant. Professor Tomar has published more than 35 books, book chapters published by national and international publishers. Recently, a book entitled Nanobiotechnology Concepts and Application in Health, Agriculture, and Environment, edited by him, with co-authored, has been published by Apple Academic Press, CRC Press, Taylor Francis, Florida, USA. He has delivered lectures in more than 75 national and international seminars, symposia, conferences, and workshops. He is member of various national and international scientific bodies and reviewer and editor of national and international journals. Recently, he has been elected as a fellow member of the Royal Society of Biology, London, UK. May I request, sir, for delivering opening remark, please, sir.
Thank you, Ashish. The chief guest of today's national workshop on advanced characterization, that is being hosted by the Department of Physics, Professor Dr. B.S. Rajput, the former Vice Chancellor of Kumayu University in Nainital, and the keynote speaker for today's workshop, Dr. Jai Singh, Professor of Physics, Guru Ghasidas Central University, Bilaspur, Dr. Mohammad Anwar, Senior Principal Scientist, CSIR Bhubaneswar, Dr. Dheeraj Singh from University of Delhi, and Dr. Rishi Sharma, Principal Scientist, CSIR CRRI Pilani, Pro Chancellor, Dr. B.K. Sharma, Aviation Retired, Pro VC Research, Dr. M.P. Kaushik, organizer of this event, Dr. Vikas Thada, the HO Asset, Dr. Pankaj Mishra, HOD Physics, Dr. Manisha Singh, ex-HOD Physics Department, faculty members, researchers, dear students, and my dear friends. I welcome you all to this national workshop on advanced characterization tools and techniques for materials science and engineering. You all know that materials are the basic substances that make up the objects. They are found in nature or made artificially. Various examples include metals, wood, glass, plastic, each with different properties like strength, flexibility, durability that determines their uses. So materials, basically, if we see, they are of two types, the natural materials and man-made materials. Natural materials, they are naturally available like wood, rock, cotton, etc. And man-made materials, which are synthesized by the humans. This includes plastic, glass, the nylons, including the nanomaterials, which are being synthesized by the human beings for their different purposes. The world is experiencing a material revolution, and material scientists and engineers have the unique opportunity to play a vital role in it. Material science engineers explore materials, their scientific fundamentals, design, and processing for real-world applications. They apply the basic principles of chemistry and physics to understand the structure and properties of materials. They design processes to manipulate materials to meet the needs of modern technology. Modern characterization tools such as electron microscopes, spectroscopic techniques, including FTIR, XRD, surface analysis instruments, and advanced imaging systems have revolutionized the way we investigate materials. These techniques have made it possible to observe atomic arrangements, detect nanoscale defects, examine surface morphology, and analyze functional behavior with incredible precision. It's very important that precision and accuracy regarding any examination is very important. Such capabilities form the backbone of cutting-edge research, enabling innovators to synthesize different nanomaterials, composites, semiconductors, biomaterials, and smart technologies. So a workshop like this serves a dual purpose. On one hand, it provides participants with hands-on exposure to sophisticated tools and methodologies that are essential for high-quality research. On the other hand, it fosters an interactive platform where experts, researchers, and students can exchange ideas, discuss emerging tech challenges, and identify new directions for the collaborative works. These interactions not only strengthen our academic ecosystem, but also enhance our institutional capacity to contribute meaningfully to national and global scientific advancements. I am thankful to distinguished resource persons who will share their expertise and insights on the advanced tools and techniques in material science. Your dedication to fostering a culture of research, innovation, and academic excellence is truly commendable. I encourage the participants to fully engage themselves in this workshop, explore new methodologies, and use this opportunity to broaden your perspective on material characterization and its applications. The knowledge you gain today will undoubtedly enrich your research capabilities and open pathways to new possibilities. I advise to organize the similar kind of workshop as a hands-on training workshop so that the participants can gain in-depth knowledge of tools and techniques being used for the characterization of materials including the nanomaterials and different kinds of smart materials. With these words, I once again welcome you all to this workshop on advanced characterization tools and techniques for material science and engineering. I wish the workshop a great success and hope it incites, inspires fruitful learning and impactful research outcome. Thank you very much. Jai Hind, Jai Bharat.
Thank you, sir, for providing an inspirational start to the National Workshop on Advanced Characterization Tools and Technique for the Material Science and Engineering. Now we're privileged to introduce Honorable Pro-Chancellor Sir for the National Workshop, Lieutenant General V.K. Sharma Sir, Ati Vishisht Seva Medal, Pro-Chancellor of Amity University, Madhya Pradesh, is an accomplished military leader and academician and alumnus of Rashtriya Military School, Chel, Shimla. He was commissioned into Corps of Signal in 1972 and served the Indian Army for nearly 40 years. Retiring at the rank of Lieutenant General, he played key roles in Operational Rakshak and Operation Vijay with Kargil War and held several prestigious commands and instructional appointments. Academically distinguished, he topped VE, ME, MMS programs throughout the academic journey and later led the Military College of Telecommunication and Engineering MO. Awarded the Ati Vishisht Seva Medal in 2011, he has traveled extensively representing India internationally. Amity University, Madhya Pradesh has been awarded as the best private university of Madhya Pradesh twice under the influential and charismatic leadership of our Honorable Pro-Chancellor Sir. Under his able guidance, right from the 2011 till today, university has grown by leaps and bounds towards excellence and has been ranked among the top 200 universities in the country in the NRF ranking. Also, Amity School of Engineering and Technology has been ranked #1 private engineering institute in Madhya Pradesh. May I request, sir, for delivering the words of wisdom to the gathering, please, sir. So you avoid.
Sir, you are on
Not
mute.
from you, sir.
Please, still not audible, sir. Not yet. You are visible but not audible, sir. Hello. Not yet, sir. Still not yet. I think you have to log out and then log in, sir.
Am I audible now?
Yes, sir.
Yes, sir.
Okay, fine now.
Right. So, thank you very much for the introduction, Dr. Ashish Preta. Professor Dr. B.S. Rajput, the former Vice Chancellor of Kumaon University, Nainital, Uttarakhand. Dr. R.S. Tomar, the Vice Chancellor. Dr. M.P. Kaushik, the Pro Vice Chancellor Research and Dean Research. Professor Dr. Vikas Thada, the Director of ASET, who is organizing this workshop. Professor Dr. Pankaj Mishra, and all the other participants who are online listening to me. The national workshop organized on advanced characterization tools and techniques for material sciences and engineering is a step in the right direction, because the entire universe, physical world that you see, everything is made of some material. And even the software, which is widely being recognized as the next dimension and for artificial intelligence, even the software has to work on some hardware, through some hardware. So therefore, the importance of materials is by no way reduced with artificial intelligence and tending towards real intelligence coming in. And for materials, there is a greater need now than ever before, with new materials being made artificially, nanomaterials coming up in a big way, that we need to do their characterization, to study their qualities, to study their strengths, to study the way they behave under different circumstances, to study their structures, and to study how these can be utilized effectively in various applications for engineering and for day-to-day life. For that, it is important to recognize what exactly do we understand by the word and characterization of materials. Now, characterization is done through various methods. As a matter of fact, I would have much appreciated if this workshop had been in the physical mode, because the characterization can truly be learned not through lectures, but only once it is done in the physical mode and the participants and the researchers are able to see what it is all about. But I can say that the techniques which are used presently for characterization, there are primarily three types of techniques. One is through the microscope, called microscopy. Other is through spectrum analysis, called spectroscopy. And the third one is through the light diffraction techniques, the amount of diffraction that is given by a material. Under microscopy, again, there are four major techniques. One is called the scanning electronic microscope, which you all know what it is. It's used for high resolution imaging of a material's surface microstructure. So the scanning electronic microscope only will tell you about the surface properties. It does not tell you about the internal properties of the material. For that, then you have to use the transmission electronic microscope, which is used for high resolution imaging of material surface structure at the atomic level and at the internal level. That means, how do you come to know how many protons are there, how many neutrons are there, and how many subparticles are there? That can be done only through transmission electronic microscopy. So that kind of equipment has to be available today in the labs, and we are lucky that even if it's not available, the virtual labs can be utilized for doing this work. The next level is atomic force microscopy. Now, this particular technique creates a 3D image of the surfaces at the nanoscale. That means you can exactly see at the nanoscale what the structure is. And of course, the last one is field emission scanning electron microscopy, which is a very advanced form of scanning electronic microscopy, which is used for even higher resolution. Now, the principle of spectroscopy is based that every body which is above 0 degrees Kelvin, it emits radiations. That is the physics law. And the radiation frequency which it emits directly proportional to the temperature of the body. So based on that, and then also it is dependent on the material structure also. So we got X-ray photography, Fourier transforms, spectroscopy, Raman spectroscopy, etc. So with the help of spectroscopy, you can identify the functional groups in a material that confirm the presence of additives. You can know what are the additives, and the spectrum which has been emitted by a pure material is known. The spectrum which is emitted by an impure material is all coming out from the experiment that we perform, and from that it is possible to make out what are the impurities and to what extent are these impurities present in the metal. That is how you come to know about all this, but these are expensive tests and not easily available at every institution. The last one is called diffraction. Now, diffraction determines the crystalline structure of a material. And of course, then there is mechanical and thermal analysis and other advanced techniques also which are available. So all these techniques need to be thoroughly mastered by the students of those who are learning material science and those who are learning about various composites, various nanoparticles, and trying to study the properties of materials under different atmospheric conditions, under different temperature conditions, and under different conditions of pressure. So these qualities make all the difference when it comes to the application of the materials in the industry. And what is more important that we are studying is the applications. New materials are being found out which are lighter, which can conduct electricity, or can act as total insulators, which can conduct heat or can stop the conduction of heat, which have got greater strength to weight ratio. That means they are lighter and provide greater strength. And adding this, some of the particles with nanoparticles enhances their strength to a large extent. And my dear researchers, a very important thing that you must keep in mind is the cost. While doing research, some of us forget that the cost is paramount importance, and we try to give solutions which are very expensive, like adding gold nanoparticles or adding silver nanoparticles. Easier said than done. Maybe that the strength increases manyfold or something happens, but then look at the cost which goes up. The cost goes up many times. So, which is not a cost-effective solution, and particularly for a developing country like India, where we are much dependent on reducing the cost. We must make sure that the solutions given by us for various materials are cost-effective. So that is the challenge for our country. Like we were able to send a mission to the moon or to the Mars, which was at a cost less than the cost of producing a high-tech Bollywood movie. That is how we gain, and that is how the world is surprised that India can do such jobs at a very lower cost. Therefore, we must be able to identify materials which are at low cost, but yet strong, effective, and useful to the engineering world. The role of universities and research institutions today is that the nurturing talent, shaping future researchers, and a strong foundation must be there. And I appreciate the works of the organizing team for having organized this workshop, for having collected the papers for that, and for having motivated the students to undertake research in these subjects. So I convey my compliments to the organizing committee and to all the research scholars and participants of the workshop, and I wish this workshop a great success. So thank you very much, and Jai Hind.
Thank you, sir, for your words of wisdom. Has always been an inspiration and guiding us. Moving forward, it is my privilege to introduce our distinguished guest, Professor Dr. B.S. Rajput, sir. Professor Rajput is distinguished physicist and academic leader, renowned for his contribution to theoretical and high-energy physics, including significant work on supersymmetry and black hole dynamics. His visionary leadership as Vice Chancellor brought remarkable academic and infrastructural advancement to the Kamayu University under the University of Excellence recognition from the UGC. He has also served as chairman of the Uttar Pradesh State Council of Higher Education and held several key national academic positions. Recipients of the Vigyan Shri Award and featured in Who is Who in the World USA. Professor Rajput's illustrious career beautifully blends research excellence with the educational leadership. We are truly honored to have Professor Rajput sir with us today. Respected sir, we are eager to hear your insightful address. Please grace us with your words.
Thank you. Am I audible?
Yes, sir.
Yes, sir, you are audible, sir.
See, I'm thankful to the organizers to invite me to participate in this workshop. So, Mr. Vice Chancellor, Mr. Tomar, Pro-Vice Chancellor, Sharma, and Professor Kaushik, then Professor Mishra, who is the organizer of the seminar, head of the physics department, and other dignitaries on the dais. So the purpose of this conference or the workshop is to bring together the scientific, educational, and technological potentials to contribute to the sustainable future using different forms of materials. The recent advances made in various innovative fields of science and the technology related to the materials like nanophotonic, amorphous material, smart material, superconducting material, semiconducting material, nano materials, and the dark matter, of course, which is now a mystery. These fields have opened the new windows for the new research at the fundamental level and provided the opportunities for recent technology advances for sustainable and eco-friendly developments. Each of these fields require a specific separate lecture, detailed lecture. I will not go to all these fields in my this small address to the audience. I will confine myself only to the fields of the material science where I have worked in last 45 years with the team of research students with me. So in this direction, the first field which we have worked in among all these fields they have mentioned is the superconducting materials. The superconducting materials nowadays, the need of the time because they can open the new window in the development of the super fast computer and particularly quantum computers. Basically, superconductivity, the property, it was first observed by H.K. Ohms, and he got Nobel Prize in 1913 for his work. What he did, he purified mercury and then lowered down the temperature. And at a particular temperature, a very low temperature, 4.2 degree absolute, it became transparent as well as the 100% conductivity. This means the resistivity became zero. When the resistivity becomes zero, the conductivity becomes infinite almost. So this thing was observed by H. Ohms first time, and it was a very mysterious behavior because before that nobody could imagine the zero resistivity in a substance. He defined this state, a new state of the material, called the superconducting state. And in this superconducting state, the conductivity is so high, almost infinite, that everybody was tempted to use it. But the temperature was so low, it was not possible to attain it without liquefying helium. And therefore, practically, it could not be possible to use it. At the same time, some other people started working on the alloys of the different metals, and they also got superconductive behavior but that also at high temperature of the range of 23 degree absolute. Absolute means this temperature minus 273 degrees, then it becomes centigrade. So it is very small, very low temperature. 4.2 is almost 270, minus 270 degrees centigrade. So it was not possible to achieve this temperature for the practical use. Then in 1986, Muller and Bednorz, they demonstrated the superconducting behavior in some ceramic substances, ceramic materials. And this behavior was at some higher temperature, like ultimately in some substances with the different combinations as high as 180 degree absolute. So it could be achieved in the laboratory, and one can work out in this. So that became superconductivity at high temperature, because the temperature at which a substance starts behaving like superconductor is its critical temperature. Below that temperature, it is superconducting. Above that temperature, it is ordinary, not conducting in that way. So in this case, there's such a substance which could show the superconductivity as achievable temperature. We call it high temperature, though it is not that high. It is still minus 120 or so in centigrade. But it is achievable temperature, and we call it high temperature superconductivity. You see, the explanation of the conductivity in mercury or the low temperature superconductivity could be made by using Milner effect, which is basically the expulsion of magnetic field from the core of the substance, the superconducting. But the explanation, and then in new theory came BCS theory. BCS theory means a Braden, Cooper, and Schiffer theory, which could explain in terms of the Cooper pair formation, the superconducting behavior of the substance. And ordinarily at low temperature, but at the normal temperature or the higher temperature, the superconductivity which was observed experimentally could not be explained theoretically. What is the theory to explain superconducting substances at high temperature or superconductivity at high temperature? So this behavior of the materials, superconducting behavior of the material at slightly higher temperature opened a new field. And then in the 9th decade of last century, toward the end of the century and also beginning of this century, it became the hot subject or the new emerging area to explain the superconductivity at high temperature. University Grant Commission selected some people from the country, some good theoreticians and experimentalists, to work on this problem. And I was also one of those people who were selected to take up this challenge to explain theoretically the region of superconductivity at high temperature. Just like Cooper pair formation at the very low temperature could be done to explain the superconductivity. But superconductivity at high temperature could not be explained. I took up the problem assigned by UGC in the form of the big project. Some projects were given to some leading people to explain the superconductivity at high temperature. And then we developed a microscopic theory at the fundamental level, a theory which we called phenomenological theory of the superconductivity. And in that, we have demonstrated that the behavior of the substances working as superconducting high temperature in terms of the quantum chromodynamics and restricted chromodynamics. Quantum chromodynamics is well known to the people working in physics and high energy physics, but restricted quantum chromodynamics is like restricted certain degrees of freedom from QCD by applying the magnetic symmetry. And in that restricted theory, the condensation of the monopoles of the ions led to the superconductivity at high temperature. So this idea of explaining superconductivity at high temperature in terms of the restricted chromodynamics using different methods of particle physics was a new thing. It was accepted very widely by the people, and this behavior of the material showing the superconductivity at high temperature could be accepted. Then this thing we did not only in restricted theory, chromodynamics or QCD, but also in the supersymmetry, dynamical symmetry breaking of the supersymmetry. Supersymmetry, when it is broken dynamically, it shows the behavior of superconductivity. Then we have demonstrated that the restrictor, the RCD vacuum, having the plasma of dione and antidions, behave like magnetic superconductors. or a new type of the superconductivity called dual superconductivity. So these two types of the superconductivity in terms of electric charge, in terms of magnetic monopole or diodes, and also in terms of the supersymmetry, that became supersymmetry, dual supersymmetry, and the color supersymmetry, color superconductivity. We have explained this phenomena of superconductivity at high temperature in different directions, in different fields, using different methods of high energy physics, and establish a link between condensed matter physics and the high energy. Establish a link between the superconducting behavior of the substance as well as the bulk behavior of the substance, and that became very hot topic. And some papers were published by different people, and 4 or 5 people got PhD in this on this work which we conducted there. So this was the work on superconducting materials and the application of the superconducting material. Why this problem was being taken up that curiously by UGC and by other group of the people working at different places. The reason was that if superconductivity is established at the high temperature, then that will open new window for the technological development. One can have superconducting computers, very super fast computer, or rather to say quantum computers can be made using the superconducting materials, superconducting switches, and behavior of the magnetic motors could be explained in terms of superconductivity at high temperature. So that was the field where the material science was being done by the high energy physicists of the particle physics. Another scope where the material science was being done by my research group was nanotechnology. So this nanotechnology is not a new subject, rather to say, for Indians, because in Vaisheshik Darshan also there is the mention of the nanotechnology also, and there is the mention of structure of matter. The structure of matter, as explained by explained in Vaisheshik Darshan by Maharishi Kanad, that explained the existence of the nanoparticles and nanomatters. This new thing of nanoscience or the nanomaterials, it can change the direction of technology, advances in a wide range of applications. So it started basically, the field was started by Feynman, Richard Feynman, in 1960 in his wonderful lecture at American Physical Society, where he described the possibility of having the nanostructures in computers, nanostructures in biological sciences, and nanostructures in electron beam lithography. So this work of Feynman opened the field, and then many people were tempted to work on that. And ultimately, all his speculations and predictions now are being proved true. Then there was another physicist, Ralph Randall, who demonstrated the electronics at the macroscopic level, and that was quantum electronics. A new field was started in some nanoparticles. That was quantum electronics, and then the two-dimensional walls with the zero thickness almost were constructed using the thin film growth technology, where one atom at a time, and that was a wonderful demonstration. So that became now, we could get zero-dimensional quantum dots. Worked out whole quantum mechanics of that. We also got quantum wire, having the nano size diameter, very small diameter of the size of the atoms. And then the plane, narrow planes means if the sheet, the two-dimensional sheet with zero thickness almost, one atom thickness or two atom thickness. So these devices open the new era in material science, and we have used it to work out quantum mechanics to explain their behavior. And we have been successful in doing that, particularly quantum dots and quantum wire and quantum planes. So some students working in my research group got their doctoral degrees in these fields also, quantum dots, quantum wire, and quantum planes, the three-dimensional. And now, then, new things were started by the end of the last century in terms of the buckyballs. The buckyballs are the nanostructures, and that they were made, and the quantum confinement was observed, and then three-dimensional periodic photonic crystals also were made, fabricated, nanotubes were also made, and the superconductivity behavior of nanotubes were demonstrated. So in these fields of nanoscience or nanoparticles or nanostructure as nanomaterials, they change the technology from fundamental physics to the quantum technology. Or quantum mechanics became the guide now for the technological development at the nanoscales or nanoscience. So nanoparticle or nanomaterial are made with the application of quantum mechanics in the material science for the condensed matter. So quantum mechanics applied to the condensed matter is possible only when we have the small size nanoscience. So this nanostructural material opens the new field of the quantum technology. Some unusual properties of carbon nanotubes are also observed, and then electronic devices, reinforcing fibers, battery technology, sensors, shielding, etc. And these quantum nanostructure can be produced now by bottom-up approach or top-down approach. And most common applications of nanoscience now will be in terms of nanotechnology, nano print lithography, scanning tunneling microscope STM, nano atomic force microscope AFM, and accurators, molecular switch, nanocrystals, and ferrofields. These are the fields where physicists can be encouraged to work in material science. Because this material science is opening several new windows, particularly smart material, for example, or the nano-enormous material, or nanophotonics. So these are the new fields where physicists can contribute a lot, and they will give the new directions to the development in the eco-friendly system, the development of the nation in terms of the technology at macroscopic level. So I always speak in terms of the quantum technology. I speak in terms of the quantum electronics, also the quantum computers and quantum artificial intelligence, quantum neural network. So these things are possible only when the system is made nanostructure system. This means size of the system may be a few atoms only, or less than that, rather to say. If one atom per system is at the ideal situation, we are going even to the electron representing the system. So in that way, the quantum mechanics is finding the application of, therefore, quantum information processing became possible because of these nanostructure quantum studies. And quantum information processing opening a new era for quantum computers as well as quantum neural networks. So I hope that some of the speakers in the seminar or the workshop you are organizing will be taking up some of these problems in their discussions. I know some people are doing work on these problems in different universities. Wherever I visit, I encourage the people to work in quantum technology. So with these words, I am sorry that I could not be visible in my address, because it is always coming when I try to open it, coming that it should be allowed by the system, and I could not get it. Anyhow, I have conveyed whatever I wanted to say in the beginning of the session. Thank you very much for listening to me. Jai Hind, Jai Bharat.
Thank you, sir. Thank you so much, sir, for your insightful address. Moving forward, let me introduce our next keynote speaker, Professor Dr. Jai Singh, sir. It is my privilege to introduce Professor Dr. Jai Singh, an eminent researcher and academician from Department of Pure and Applied Physics, Guru Ghasidas Vidyalaya, Central University, Glasgow. With over 12 years of teaching and 15 years of rich research experience, Dr. Singh is widely recognized for his significant contribution in the field of energy materials, oxide materials, 2D nanomaterials, nanofabrications, and luminescence material. Dr. Singh completed his PhD in physics from Banaras University and pursued postdoctoral research. So we have to wait. I think Dr. Jai Singh sir has not been joining us, is not joined us yet. So we will wait for him. Sir, we can't hear you if you're talking close. Sir.
Yeah, Professor Dr. Vikas Thada, can you hear me now?
Yes, sir, you're audible.
Yes, sir. Yes, sir.
Okay, so I'm just telling that I would like to log out now from here. So you can continue with the workshop when the speaker joins, because I got some other work to do, and then 12 o'clock also we got the presentation for which here in the PhD. So I'm logging out from here. Thank you.
Yes, sir.
So Pankaj, I think I should also log out. Any thing required to be done now? I think your
Yes, sir.
introduction has been done now. Okay.
Yes, sir. Thank you
All
very
the
much.
best to all of you.
Thank you, sir.
Take
Thank
care.
you, sir. Thank you.
Bye-bye.
क्या इशू क्या है प्रोफेसर जयसिंह का? Why he is not able to join?
Sir, joining issue हो रहा है उनको, but he is joining from other device. Jai Singh sir, good morning.
Hello, can you hear me?
Yes, sir.
Yes.
Good morning. Yes, we can.
Yeah, my slide is visible first.
Yes, sir.
Is it moving?
Yes, sir. Yes, sir.
Yeah, great. Thank you. Yeah, please start.
Ashish, sir, please start.
Yeah.
Yes, sir. Moving forward, let me introduce our next keynote speaker, Professor Dr. Jai Singh sir. It is my privilege to introduce Professor Dr. Jai Singh, an eminent researcher and academician from Department of Pure and Applied Physics, Guru Ghasidas Vidyalaya, Central University, Bilaspur, Chhattisgarh. With over 12 years of teaching and 15 years of rich research experience, Dr. Singh is widely recognized for his significant contribution in the field of energy material, oxide material, 2D nanomaterials, nanofabrication, and luminescence material. Dr. Singh completed his PhD in physics from Banaras University and pursued postdoctoral research at prestigious institutions including Pusan National University and Sejong University, South Korea. He has exceptional research record with 158 publications, over 3,900 citations, an H-index of 36, and numerous high-impact work in leading journals such as ACS Applied Energy Materials, Chemical Engineering Journal, Nanoscale, Scientific Reports, and Applied Surface Engineering. He has successfully handled 4 major projects, sponsored research projects worth approximately 1 crore, several industry-funded projects, and served as a co-PI of the DST PERS project valued 8.57 crore. His academic leadership include guiding PhD scholars, mentoring postdoctorate students, and contributing to the multiple national and international committee. Professor Singh has been honored among world top 2% scientists in 2023 by Stanford University and has received several notable awards, including Young Scientist Startup Research Grant DST Serve and recognition from the international journal and scientific bodies. He has also served as a visiting scientist in Germany and reviewed numerous PhD theses, government R&D proposals, and international research projects. May I request Professor Singh sir to deliver the keynote address, please, sir.
Okay, thank you very much for your kind introduction. Before I start my talk, I thanks to organizer, especially Professor Pankaj and Professor Manisha ma'am, for his kind invitation and deliver this talk. Basically, I visited your institute, I think, 2, 3 years back. Very nice institute. Okay, come to on topic. Topic is that today I will discuss about this wonderful instrument. This is known as the electron microscopy. Basically, I will discuss about the one of the this scanning electron microscopy, that we can measure the surface of the system that we cannot see the naked eye. That is very important. So there is several important about this instrument and utilization of the important. This is not for only for physics. This is used for the all science branches in I think life science, chemical science, as well as the engineering science. So many people are using for this instrument to characterize your sample, as well as this instrument is right now is a powerful tools, as like the for the you are making some device and any more informatic and that. So before this, this is some outline of this talk. I want to cover that how that we use the electron microscopy, how can get the image, and most important sample preparation, as well as the that component of this instrument. If time will be allow, to some software, how to handle this software, how to use the software to find out the particle size, as well as the histogram of the system, that I want to cover here. Okay, I think right now we are in era of the material science. I can say this in material science is that is very important. Nature is a god that is preparing the sample in a form of the different structure, different sizes. So that sizes and structure, that will be some processing. What we are studying in the material science, first we synthesize the materials in our lab as well as the in different manner, then move for characterization. There are several tools for characterization. That is, one is the structural characterization, and there is the spectroscopic characterization. Then we move further this for microstructure and nanostructure. Then we show the property, optical property, magnetic property, thermal property. Huge number of property are using for the different applications. So for lastly, we move for the application. We make the device, solar cell device, yeah, sunscreen, or any types of devices we are making for the basically we are right now in gadget time. So that sample creation is generally two techniques we are following. This is the microscopic and spectroscopic technique. Is a microscopic techniques is very interesting about this is the interaction of matter with electron. That we are how to in matter and electron by we interact with that we after the interaction there are several phenomena will be occurred. And a spectroscopic technique that will be completely interaction of the matter, photon, and light. I think in the next two talks they will cover to about this matter of the light in during the Raman lecture. Maybe Mr. Dheeraj will be cover this topic in detail, and more. And one other speaker will be covered the structural that will be followed by the X-ray diffraction. And also we can find out the structural diffraction with the transmission electron microscopy. But I will not little bit I will cover this topic. Basically, so that in microscopic there we want to see the structure of the system, surface structure and internal structure of the system. So basically in a surface structure for the that we can say this is a quality and quantity information we can collect by this scanning electron microscopy. And transmission electron microscopy we can find out the internal structure of the system and crystal structure of the system. The more detail we can find out the with transmission electron microscopy. So both electron microscopy techniques is very important. Then I will next slide I will describe the detail about this and the microscopic techniques. So in spectroscopic X-ray XPS is the UV visible spectroscopy, FTIR, Raman spectroscopy. The huge number of spectroscopy techniques is available that you can utilize for your find out the quality of the sample as well. And also you can correlate with this transmission electron microscopy, scanning electron microscopy with the help of this spectroscopy technique. So that why we need this electron microscopy. One of the important question of this obviously. So there are several limitations of our eye. Our eye cannot see the near the 25 centimeter, and also that minimum that we can see the thickness of the eye are this only 0.1 millimeter. Beyond this, we cannot see our naked eye. For further, we have developed this light microscopy, and light microscopy we can see some micron size, and that will be nearly 0.1 micron to I think 0.2, 0.5, depend upon the source of the system. And another microscopy is the electron microscopy, and here is that we can see here the some nanometer to angstrom level. So that is very important about this. Basically, our several things about the virus, DNA, and atoms that will be exist in the nano size and angstrom size, so that we can use this technique, find out the in detail about our the nature, how to develop, how to create the system atom to atom so that techniques is very important for the detailed information for this. So this is definitely this is a very expensive instrument, and nearly cost is 3 crore to 10 crore rupees right now in Indian rupees. But typically, if you think about the battery in an electron volt, that will be, we will describe about how to use this. So there are some books in the this for biological purpose and as well as the material science purpose, and many more wonderful books available on this topic. So that microscopy is very important. Microscope that makes it much easier to us to view and understand very small object very clearly. That is very good. So there are three types of electron microscopy is available in the market. Basically, previously in a class 10th and 12th, we have used the optical microscopy and compound electron microscopy. And further, we moved the at the PhD level, you have used the electron microscopy. And one of the most wonderful microscopies is scanning probe microscopy. In this family, the wonderful instrument is a AFM, atomic force microscopy. So that is very important. And optical and electron microscopy, that will completely involve the same physics that will follow diffraction, reflection, that will be, and sometimes that electron microscopy is a scattering and many more information. But scanning probe microscopy is very wonderful technique. That will be, that is nothing, that will be interaction of the scanning probe as well as the surface of the object. That will be, so that will be atomic force microscopy, magnetic force scanning, tunneling microscopy. So whole these types of scanning probe microscopies, there is a large family, very big family. Basically, I will cover only the electron microscopy. That is another important topic. So in optical microscopy, we are using the visual light as a source. That will be your optical microscopy have the some lenses. There is objective lenses and many more is some aperture and many more photography plates that will capture. And that will be simple things about this. There is, you can see here this optical microscopy. You are using the to section of the frog and onion in a class 10th, but that will be utilized for the, there is several things right now, too much magnified, and that image you can see, but not less than 500 nanometer and many more that you can observe by this optical microscopy. So there is basically what is need of this electron microscopy. So there is some limitation about it. Basically, limitation is that we cannot see this system or any optical microscopy beyond, as I told you, beyond 2.2 micrometer. So that is limitation about that. There is some optical elevation. This is a resolution of this is the resolution is very important. D is equal to is directly proportional to lambda upon 2 and lambda is your wavelength of your light. Basically, if you find you are using the optical microscopy, in optical microscopy you use only visual light. Visual light wavelength is the 400 to 800 nanometer that we are using the. So there is several aversion, and that due to that we can not as like the theoretical value, but approximately we can find out the 0.2 micrometer in there. So that is very important about the resolving power or resolution. Two things is very, so that actual size that will be is completely different, but by the naked eye, by the optical microscopy, we cannot see the find out the actual size. Due to this, there is some, we can find the overlapping. So there is the you think about only simple things. You have two finger you can join, and there is you cannot find any hole, but you use the hand lens. Otherwise, you use the optical microscopy. There is a big gap between this. So that gap we can not visualize so due to this our resolving power is not higher as like the optical microscopy. So that is totally depend upon the wavelength of your source of that. So that you can see here there is unresolved system and resolved system. That resolved system is actually that will be looks like this, but due to the resolving limitation of that, we cannot see the actual image of this. So there is the magnification of that system is in a class 10th. You have find out that actual size of the image and actual of the object. So that will be system. There are some listed I have here. There is a light microscopy is we can see only 1000 times magnified, but electron microscopy you can see the 5,000, 50,000 to 1 lakh times. In a scanning electron microscopy, just half of the transmission electron microscopy. So right now, that is the best effective magnification we can achieve by the, so that is the, as like the, we can convert the in the length and distance that will be. So there is some that is most important about the discovery of this electron microscopy. After the discovery of the quantum mechanics, and thanks to de Broglie, thanks to Bragg's, that we give the wonderful equation and wonderful information. And after that, we can find out that we set some correlation between the matter, means your electron and waves. That is wonderful equation. Lambda is equal to h by p. Lambda is the nature of the, generally we know this is a wave nature, and p is the particle nature. So with the help of this dual behavior, that with correlation of this wonderful equation, lambda is equal to h by p, we can correlate the, we can think about the electron is also behave like the wave. That is this wonderful equation that we can find out the more information, very good information, or that we can magnify your system. So there lambda is that is wonderful equation that will be also lambda is equal to 1.2 under root v. V is the potential, that excessive potential under root v nanometer, that will be give the, that we can increase the voltage, then we can decrease the wavelength. Then with this information, with this equation, we can tune the, we can find the lower wavelength of the your electron, and as well as the, but as in optical microscope there is limitation. We cannot tune the 400 to 800, we cannot decrease the wavelength of, but in electron microscopy we can decrease, we can find out the, as per our requirement, wavelength we can change by the accelerating voltage. So this is important of this electron microscopy, and beauty of this electron microscopy that you can utilize for the find out the, we can see the lower size of the your object. So there is limitation is that equation that I said d is equal to 0.6 lambda and n sin alpha. So that n is that this is a aperture of this. So resolving power is directly proportional 1 by d. So that will be that. So resolution is nanometer. That will be also, and with the help of this, then this electron microscopy is a very wonderful tools, and that will be get the more information or detailed information as the microscopic topic, as nano size so then you can see here, if we are using the 100 kilovolt of the source of the accelerating voltage, then we can achieve the 0.24 nanometer of the wavelength of the system. That is very important. So actual resolution and the that you can see here, there is some, if that will be changed, the how to that high and low magnification, that will be so definitely. So if you want to find out the good resolution, the resolving power of microscope is very higher. So with the help of that, we can see the very smaller size and many more. So basically there are two types of electron microscopy, in transmission and in scanning. And transmission is completely different, but we can also see the size of the materials, and also internal structure. So that for this there is several limitation about the transmission electron microscopy. We can find out we can use only the 100 nanometer thickness of your material, we can observe only. Otherwise you use the more thicker material, that your electron will be absorbed that material, you cannot find the internal structure of the system. But in scanning electron microscopy is completely in a different manner, that will emit the electron from the surface in different manner, that we can use the that will be, there is no matter of the size, we can use the inch size of your materials, that you can utilize. And so due to this, scanning electron microscopy is a very wonderful tools, and then we can further this there you can see here this light microscopy and transmission and scanning. Light microscopy and transmission looks like the same. In a light microscopy there is some lenses, condenser lenses and objective lenses, eyepieces, And the same in transmission, there is a lenses in the conventional lenses and arbitrary. There is, but that lens is not as like your light microscopy, but that is, I told only that this is a lenses. This is a electromagnetic lens. So I will describe in detail about this lenses. Basically, the same lenses using in the scanning microscopy. In a scanning microscopy, that will is using the condenser lenses. There is the scanning coils, and there is the two different types of, then we can use the different type of detector, and that detector is limitation about this, and that will be scanning the rest of the system, and in the selected area that that you can find out the in as by the this signal, how to collect the signal, and that we can get the find out the image that you can describe in detail. So that resolution of this electron microscopy, basically in a transmission microscopy, is the generally 40 to right now 300 kilovolt electron microscopy is available in the market. Scanning electron microscopy, we can use the in a same microscopy in a 1 to 30 kilovolt. Then effective the transmission is a prop 1 angstrom we can see. But technique, but cost is very high, nearly I think so more than 10 crore in India rupees. And effective estimate of the resolution of the SEM is that nearly 1 nanometer. There is by eye we can see the 0.1 millimeter, and by the electron microscopy, by the optical microscopy, we can see approx 0.1 micrometer, and by the same 0.1 angstrom. So that is the totally, you can see here the how to we can resolve our resolving our the instrument is more and more, and we find the detail at the microscopic level. That is this is the system will be completely that will be structural as well we can get the chemical information point by point by the we are in testing region, which region we want to select, which region want to find out the that is the one of the. And also this is a as I told, this is a very powerful tool to characterize the all range of the or the living cells, non-living cell, and the insulator system, conductor system, any types of system that we can observe from nanometer to micrometer length. We can observe, we can find out the this is. So there is definitely that market is going to boom, and you can see here that is not only using the in the life science, material science, semiconductor, nanotechnology, other applications that you can see the I can quote it in different colors, and market is going too much higher, nearly $10 billion US billion dollar is right now moving in the market. So there are huge, and yearly 8.6 percent that will be increasing. So variety of that will be application due to that instrument is very powerful instrument, as well as the market of the instrument. You can see here the beautiful hair of the woman that how can see how looks in the scanning laryngoscopy, that you can see if you resolving this hair, basically in South India, that is too much very big industry about this you can see here the same images of the system, and that looks like this. Then you can find the quality of this here, and that you can see here. So there is in the lower that you can see there is scale, and there is some magnification is there is x is even that is how much they magnify, and there is some kilovolt that which power with acceleration power that will be utilized. So this type of information you can find out that this scanning laryngoscopy. So then you can know the quality of the hair and many more information that you can get. There and the same things that will be I told you in the magnification, the same how to magnify your system in SEM. That will be definitely that is the image of the length and scan of the length that you can divide by this, then you can find the magnification of your instrument and SEM, especially in I'm talking about the in SEM. So that there is several images. I will give you some very beautiful images and that information. some is the transmission electron microscopy, and another one is the right hand side is the scanning electron microscopy. This first is the optical microscopy. You can see the blur of the structure, and further we can magnify our, if you have the very good tool, that with the help of this wonderful tool electron microscopy in a SEM especially, that you can see here in a SEM, that will be looks like some wires like structure. And again, we can put in a transmission electron microscopy, then you can find some rod-like structure. And further we move for this is you can see here the wonderful information about this is known as the HRTM, high resolution transmission electron microscopy. This you can see here atom by atom, how to arrange the atom, how to behave atom. There is some stacking fault. There is, so then you can conclude them. If you want to find out the detail, you can correlate with property as well as that will be your as sensitized material. That will be, without this information you cannot correlate our microstructure, that property that we cannot correlate. So due to that, this techniques is very important about this that you can find. So there is another electron microscopy image. You can see this is the COVID-19. That is looks like electron microscopy. Some picture is the computer generated, but image first is the real image of the coronavirus, that you can see here how to looks like in transmission electron microscopy. And this, there is some other materials how to look. That's, as I told you, atomic force microscopy. This lever, cantilever, is tips like looks some ant head, blood cells, and then another diamond-like thin film, and this. So there is some I want to describe about the history of this electron microscopy, and more interesting history of this microscopy family. In 1930, after the discovery of the quantum mechanics, that Ruska, that who was invented is the electron microscopy, and 1935 that will be electron microscopy was that will be used for different purposes. And 1935 the null that will be that he want to develop to scanning electron microscopy, but commercializes the 1960 after the 30 years later, 1965. So this more complicated instruments is a transmission electron microscopy that was discovered in 1930, and less complicated instrument is scanning electron microscopy that was discovered, commercialized in 1965. And more important, in 1985, another instrument is that discovered is the AFM, atomic force microscopy. That is not too much complicated, very simple phase that will involve only the Hooke's law, F is equal to minus kx. With the help of this, so that is important things. If you know the science, that you can develop the very wonderful techniques, wonderful instrument for the different purposes. So that is very important about this. So that as I told, this is the first commercial is a Cambridge scientific instrument that was developed in that time. Is a resolution is not too much good. I think 50 nanometer and that. But right now we can see 1 nanometer this resolution of this. So only this is a completely analytical techniques. As I told, is quality and quantity both that will be. So there are several Nobel prizes awarded and this microscopic techniques, and recently by the cryo-EM and the atomic force microscopy was that we also received the Nobel Prize. So 3 and 4 Nobel Prize are people are receiving. So this is the first electron microscopy that you can see here, 1935, and this is the first scanning electron microscopy that you can see here. But right now this that is located in my place. This is called Zeiss company, and this resolution is 2 nanometer, 3 nanometer at 30 kilovolt. And there is some source I will tell in detail about this. So there is different scanning electron microscopy model that will be available in the different developed by the different company, and some Geol and Zeiss and one more Thomas, many more. So that you can see here. So there is some limitation about this instrument and more information. And also that we can one more attachment is in this instrument. This is the EDS, energy dispersal X-rays, and this is also that you can use this. And the FEI company that is earlier, that will be Philips company, that will be a wonderful instrument that will be there. So that you can see here, this is a very beautiful images of this zinc oxide structure. Without the SEM, we cannot find out of this beautiful structure at the nano level. So after the discovery of this scanning microscopy, with the help of this scanning microscopy, that we can find this beautiful image that is developed by our lab as well as that. This is also developed by the nature, that we can find out this different types of wonderful structures, this nano layers, nano kites, nano flowers, nano tubes. And this is materials is MAPB3 is wonderful materials. This is used for the solar cell material, and this is a perovskite solar cell. This is a mixture of the organic and inorganic materials that you can also use. That any material you can observe by these techniques. So that most important techniques to come to points. This is the how to sample preparation of this, how to put those that we utilize the same for the detailing means instrument details. I want to discuss with you. Okay. So that if you there is not too much bigger instrument, there's a tabletop instrument. Right now, two types of instrument are available. One is the very tabletop instrument. One is the bigger one. Tabletop is also good for the nearly cost is 1 CR is I think so. Okay. That when we open the chamber of this sample chamber, so there is that is some you can see the stop. How to utilize this stop is looks like different sizes. This and that on the step you can mount your sample, and that will be. And further then we move further. If your material is not conducting, then you coat some gold and silver, platinum, only the conducting purpose, not anything. That thickness is only some external level or yeah.
Jai Singh sir, sorry to interrupt you. Could you please summarize, sir?
What?
Could you please summarize, sir?
A complete lecture.
Maybe you can wind up within 5-10 minutes, sir.
Okay, no issue. I will wind up. Okay, so this is one wonderful that instrument. This is the simple preparation for the biological, especially that will be that is some carbon and fixation, dehydration, drying, and coating. With the help of that, you can find out how to prepare your biological sample. This is one of tedious job for biological purpose, but for any material science, that is not too much. That the breast cancer cells, how to looks like in the same images, and other biological materials that you can utilize, and that is a complete process of this your sample preparation technique. And there is the coating. Coating is very important. If your system is a non-conducting, then you coat with the that system. So there is some protocol for this. There is the 6 step for this fixation and dehydration, drying, mounting, and sputtering of this system. The complete this is especially for that. In the scanning microscopy, then we can find out the topography and morphology information. That will be, and also utilize for chemistry purpose, crystallography orientation, and orientation of grain. Right now, people are using for the in situ experiment, that you can visualize your system in the reaction with the atmosphere, reaction with the different temperature. So that will be easy to sample preparation and big sample. So that, and also you can tune the temperature and you can modify the temperature your sample. That will be, so there is some more important, that is the high depth of focus of the instrument. That will be any other. So that will be very important about this. That if you magnify your sample nearly 1 lakhs or 10 lakhs, so then you can cover the area only 100 nanometer square. That will be very important. So here optical microscopy versus the SEM. SEM, that will be, SEM is very good for this high depth of focus compared to any other instrument that will be. So there is another carbon nanofiber and in situ experiment. So that in situ experiment, that will be if you basically any for example iron in the presence of water vapor or moisture, that will be held back which types of this I am taking the chromium oxide. The chromium oxide at different time, that in the presence of the water molecules and high temperature, that after initially and after a long time, that will be some several grains are developed. So that will be about this. So how do SEM is work? We are using the lights place of this electron and beam of the electron. There is the top of the system. There is the known as the filaments, and this filament is the tungsten and LAB6. And next will be followed the vertical path. There is lenses, as I told you, lenses is not like the glass. There is the virtual lenses is made by this is the behaved as electromagnetic lenses. Very simple physics is involved about this, how to tune this electron beam, and we can magnify, we can increase the size and decrease the size and tune the size, and that will be, and also we can, there are two important things, that when your matter is interact with your sample, there are several phenomena. We are interested only the secondary electron and back electron, and third one is the emission of X-ray, when and finally we can detect this secondary electron and back scattered electron that will collect by your detector, and further that will move for the and the CPU processing, that will find the and final image of this. So I want to conclude here. Basically, there is very long. This is nearly 1.5 hour lecture. So the next time I will cover about this. Thank you very much. If you have any question, that is good for me and good for you, that I want to describe here. Okay.
Thank you, sir, for your insightful and inspiring keynote address. The session is now open for the query and discussions.
Any question? I think basically there are several problems this instrument. Basically, if you use this, how to find, how to utilize find out the size and many more information. For this, there is ImageJ software. ImageJ software you can easily available, freely available. With the help of this, you can find out the histogram of the, and that you can also size of the your as well your rod and any nanostructure that you can calculate by. So there is and also that will be most important things about this instrument. That is, your material is creating or developing different number of electrons. That number of electron is that collection of electrons, and at different point, so that we can transfer in the image form. Then in the next slide, I will in the next time I will describe to detail. If anybody want to learn about this technique, then definitely I will help about in detail about this techniques.
Sir?
Yeah.
Good morning, sir.
Very good morning, Nirvan. Yeah.
Sir, you can continue now, because HOD sir have instructed that the speaker can continue as per discussed in the M2M. Na? So you can continue, sir, if you want to add something more.
Yeah, but no issue. I have no issue. If you can, before 5 minutes, you can
Yes,
stop. Okay.
hello.
Okay.
Yes, sir.
So, how do we get the image? That is very important. That I told you, there is the matter and electron interaction. That is, so there is this. You have seen very beautiful images by this instrument.
So you
Okay.
have to share the screen. Your screen is not shared.
Okay. I think maybe give me 1 minute. Okay. Right now you can see my screen.
Yes, sir. Just put in presentation mode. Thank you, sir.
Okay. Okay. 1, 3, 4 slide. I will conclude in 5 to 10 minutes, not more than. This is very important information about the audience. Basically, how to electron and matter will be interact with the at different levels, and that is very important. When your electron you can generate by the electron source. Source is the with the help of there are two types of thermionic emission as well as the cold emission. This is the tunneling phenomena. So that electron will be interact with matter, and that will at different level you can generate the different I think types of at nanometer range. One is secondary electrons, and more deeper is I think 100 nanometer pulse. Then back is cutted, and deeper this is looks like the X-ray. This is micron. This is, with the help of this you can find out the chemical structure of your system, and the whole detailed system that you can find. That will be how to that. So there is interaction of this matter and electron is very important and interesting about. So if your system will be if your system will be thinner, your material is very thinner, that electron will be transmitted, okay, without any interaction. So that will be you can get from the you can find out the internal structure of your material. And there is a diffracted electron that we can find out the as like the X-ray diffraction. The same we can find out here. That will be you can find out that will be d-values and atomic structure of the system, and so whole things that will be in and also one of the more important system in the cathodoluminescence. This is the visual photons that you utilize your screen. Television screen, and that will more techniques that will be definitely totally depend upon the how much your system will be generated the visual photons that will be utilized for. So there how to get the image that you can see here. I want to conclude this is my last slide. Okay, then you can select the area will be selected in the this is the some you can see here. Then in the square side this is nothing, this is the pixel. Okay, then this at the one point that your beam is rustering, and at that point there is your the system that area will be generated some number of electrons, and that is the completely approx 156 electron. Thinks about this example, and another area your raster electron beam will move, and that will be interaction of the your electron beam and surface. That will be your that will be generated 288 electrons. There is number of electron will be completely changed, and more and different area that will be, and the interaction of the electron beam, and that will be your area. That will be the number of electron will be changed. So same things will follow the whole point, and point by point, if there is no electron emitted, there is some blank, and is the number of electron is the depend upon the height of the system, atomic number of the system, and that will be also more information you can find though. So we can find the detailed image with the help of some software, then and help of your detector. Then you can find out that detailed information, deep information of any material. Those same things will be follow in the same manners, and that will be so there is some the get the image of the detailed image of your materials as well as there is some components about this. There are 7 components that we so right now I want to conclude here. That will be I think okay for me. And anybody had the question, then definitely I will give the more detail and more information about this instrument. Yeah, please.
Anyone is having query, then he or she can ask. I hope everybody had understood the topic you have explained, sir. Thank you so much, sir.
Okay.
With that enriching and inspiring morning session, we now take break for the lunch, and we will join again at 1 p.m.
Sir, we can
Thank
take
you everyone
questions also from chat
to
box, no?
join us in the inaugural session. Have a great day ahead.
Ashish sir,
Yes, sir.
we can take some questions from chat box. Few participants are asking, writing something, na? So if you can convey these questions to sir, then it would be good for the participant.
Okay,
There
okay.
is several question. Okay.
Yes, sir. Yes,
Yes,
sir.
yes.
Sir, you can
Yeah,
also,
fine. Okay, okay.
sir, you can
Hello,
also
sir.
directly
How to
exit the
gold
chat
code?
box. Yes.
Okay. For the coating, there is very simple instrument. This is sputtering. There
Yes.
is we are sputtering techniques. There are and with the help of that we can generate the plasma of the your gold, silver, platinum. Okay, basically gold, silver is a very good conductor. So there is with the help of this conductor, and that your if you are using the any materials or insulating materials, we coat that easily we can see the surface of your system, and that will be easily that gold and silver will be generated the electrons, and that we can capture the electrons and visualize the actual surface of the your materials. The coating is very important about this and the I mean you difference same and EDX in term of the scanning. Okay, EDX is the is a additional system you can utilize in scanning microscopy and transmission microscopy both. That instrument is the additional. This is a only work as the X-ray. X-ray that will be generated your system when electron and matter will be interact. There are several phenomena you can see here that will be when electron will be generated deeper side. Okay, and deeper side that will be generated the X-ray. That X-ray you can utilize the for the chemical composition that will be, and both the additional instrument that will be used in the TM and SEM in both. There is no, I think, there is no. So that is if non-conducting coating applied on the any silicon wafer, then you have coat gold over the coated substrate. Yeah, if you have a non-conducting surface in I think there are in silicon wafer and also that you can coat with gold and silver, and also somebody are using the carbon tapes is also good for the that will be. How does the working aperture in the magnification? Yeah, Suraj is very, I think, very deep in the next to next slide. Okay, aperture and how to working aperture magnification in the there. Aperture is a very important part of this SEM. Aperture is a tune the electron beam and convert the path, and very important things about this that your electron when in inform electric field and magnetic field there is followed the helical path is very important. So and also aperture, and then we with help of this aperture you can tune the and intensity of your electron beam, and that if you directly use this high electron beam, that will be your sample will be burned. So that aperture is very important, and tuning this electron beam, and that we can want to at lower magnification of the you want to see your object at lower magnification. So aperture is very important for the in scanning and as well as the, in transmission. And another question is if gold coating is applied by the sputtering, this is very expensive method for the simple preparation. Yeah, definitely. Basically, this is too much. Another techniques is the spin coating, but you have, I think, very good expertise about this. Without expertise, if you code the some micron size, there is no meaning. Only you find the information of the your gold and silver. Not you cannot get the information of the your materials, right? So there is techniques is very important. Sputting is technique is we can I think external level to nano region, we can coat your sample, and due to that, this technique, this spectrum technique is utilized for only in the scanning electron microscopy for this purpose. Okay, and one other question is Muskan Sharma. Please let me know about the image J software. So, which extent is accurate by the manual measuring? Yeah, very image software is using the in different area. This you can Google the image J, and that is high accurate information you can collect, as well as the measuring the by the manual measuring. If there is a, I think there is only I think there is no I think so, error about this image J software. You can say 1% to 2% only error, but is manually you can very image is definitely will be higher 20% to 30%. So that is very important. And again, Rajesh, gold coating top of the surface does not affect the actual. Yeah, definitely. As I told you, Rajesh, you can think about you have finger. Okay, in a dark area, there is you cannot find the image of your the finger of the, but you can some sprinkle. Okay, there is some speckle that you can go in a darker area, that will give the some lights from the your speckle area. The same things will be given the, and you can also find out the your image of the your finger. The same things will be given the this coating. Coating is only give the actual image, yeah, more informative image of the your described surface as well as the. So that is very important question, Rajesh. Definitely. So I told you this thickness and okay, आइए actually this coating and coating thickness is very important about this. Okay, Rajesh. You will get the more information, Rajesh. You can take my mobile number, then you can directly you can call to me.
Sir, one more question is in chat box. Can you differentiate in terms of working principle between SAM and energy dispersive spectroscopy?
Yeah, totally different. I told you. The same is the basically it's a we have backscattered, and that will be electron generation. Okay, that electron generation two types: secondary electron and backscattered electron. There is for both is different detector. Okay, so that in EDX is the that will be generation of the X-ray. X-ray generate from the inner circuit of the inner part of the your materials. Okay, there from the atomic structure you can think about the KLM cells, and then you can generate the inner electrons, and that upper electron will be jumped from the that inner side. For example, there is you can anyhow you can inject the k electrons, and that so definitely m electron will be jumped from the that will be you can find the energy. Okay, E1 minus E2 is equal to h mu. That energy you can utilize for the EDX. Okay, so every material have the own characteristics, own X-ray. So that is totally different manner. As I told you, scanning electron microscopy, there is additional attachment of the EDX. Okay, and also you can use in transmission electron microscopy. Yeah, any other question?
No, sir. Up to now, this is okay. Thank you so much, sir, for your valuable answers and session.
Okay.
So, Ashish, sir. So, ma'am, over to ma'am, Dr. Manisha, ma'am. मैम आप कुछ बोल रहे हैं? म्यूट है मैम आपका जो आशीष सर.
Hello.
Yes, sir.
I think anyone has not left asking questions. Sir has very
आवाज नहीं आ रही थी तो आप एक बार पूछ लीजिए.
हाँ, अच्छा मतलब अच्छी शायद थी.
okay. I would like to thank you once again, sir, for your insightful, inspiring keynote address. And with this enriching and inspiring morning session, we now take our lunch break and we will join again at 1 p.m. Thank you everyone to join us in the inaugural session. Have a great day ahead. Thank you, sir. Thank you once again, sir.
Okay. Okay, bye. See you.
Thank you so much, sir.
Okay, sir. Bye.
Session of the National Workshop on Advanced Characterization Tools and Technique for the Material Science and Engineering. A very good afternoon and cordial welcome to all once again. I, Dr. Ashish Singh Parita, welcome all to this second session of National Workshop on Advanced Characterization Tool and Technique for Materials Science and Engineering. To formally begin the session, before inviting our distinguished speaker, Dr. Mohammad Shahid Anwar sir, I have the privilege to introduce him to the gathering. Dr. Mohammad Shahid Anwar is the Senior Principal Scientist at CSIR Institute of Mineral and Material Technology, Bhubaneswar, where he leads the ferroelectric and piezoelectric materials and devices groups. With a PhD in physics from UGCDAE Consortium for Scientific Research, Indore, Dr. Anwar has over 15 years of research experience in the field of smart energy materials and device development. His research focus on the ferroelectric and piezoelectric, thermoelectric, and the advanced coating using PVD and electrodeposition technique. Dr. Anwar has published over 160 essay index papers and received multiple recognitions, including the Madhya Pradesh Young Scientist Award, the prestigious Bhaskara Advanced Solar Energy Fellowship in 2019. He is also actively involved in mentoring doctoral and postdoctoral students and in leading nationally funded projects from CSIR, DAE, BRNS, and SERV, ANRF, MOES. I will invite our distinguished speaker, Dr. Mohammad Shahid Anwar, to address us.
Yeah, thank you, Dr. Ashish, for giving me an opportunity to present some of my work out here. Okay, so I'm audible.
Yes, sir, you are audible. Your voice is very clear, sir.
And presentation is in full screen mode.
Yes, it's full screen mode, sir.
Okay, so let's formally start my presentation. So before starting, I would like to thank Amity University and all the organizers for giving me an opportunity to discuss some basics and some results of my work, what we have achieved, and just interact with the participants who all are present here. So I'll be talking something about X-ray diffractions. I think application of X-ray diffraction in material research, what we are doing it extensively here in IMMT. So I'm working in CSIR, Institute of Minerals and Materials Technology. So you might be aware about CSIR, may not be about IMMT, but CSIR. So I'll just give you a brief of CSIR. CSIR is an research organization or is an establishment of pre-independence era. It was established in the year of 1940 by the visionaries like S.S. Bhatnagar and other eminent personalities. Right now, since it is a registered society, so we have a president. The prime minister of our country is the president of the CSIR society. Vice president will be the minister of science and technology, and the DG CSIR is the secretary of the society. So everybody might be aware about CSIR. Our presence can be found in all the tick and corners of our country, from east to west, north to south, from minerals to materials, from sky to earth, from Himalaya to oceans. Everywhere you can find our presence in all the areas, whether it is physics, chemistry, biology, chemical sciences, engineering sciences, oceanography, whatever area you can think of, you will find our institute which are working on those area. Okay, so we have, apart from that, you will find lot of you cannot imagine the country scientific position without the presence of CSIR. Everywhere you will find some or other products related to CSIR, product, process, material, minerals, whatever thing is out of CSIR. But if I'll talk very much specific about my institute, CSIR IMMT, here is also versatile. So I work on material chemistry interface department. So here also we work on mainly chemistry, but apart from that, metallurgical is another area. Central characterizations we are having. We are working on mainly on minerals. Minerals means mineral processing, mineral extraction, electrical processes, hydroelectrometallurgy, all the aspects of mineral extraction, beneficiation, whatever you can think of related to minerals. We are the leading institute of our country. Okay. Apart from that, environment department is taking care of all the environment aspect of minerals and minings. Whatever things are environmentally impacting, those studies we are doing, and we are finding the remedy out of those ones. Okay. Societal and other things are there. For those who are a student or who are interested in research, they can come and visit at Bhubaneswar. And apart from that, those who are joining PhD, we are having all facilities related to a good research institute, related to social life, related to personal development, all kind of things we will find it here in a single institute, single premises. Okay. Apart from CSIR, if you since I am giving say, this presentation or this lecture is in and around here in Gwalior, so I have given some of the research in and around Gwalior, which we are working. See, Bhopal is there, which is working mainly on materials, different kind of material and processes. Niri Nagpur is there, which are working on environment. CMAP Lucknow mainly on aromatic plants. NBRI biological lab is there, biological NPL is there, on which are working on all aspect of physical sciences and standardizations. NCL chemistry laboratory, CDRI drugs related work are going on. Apart from that, lot other institutes are there, whether CRRI. So all those who are interested in any kind of research or want to join research, they can go visit, see those labs, and find some places out there, or can start their careers in this one. So just will come to our work, application of XRD. So right now everybody knows there are 7 crystal systems, or Bravell lattice, or this copper is FCC, or something is BC, something. But how? What are the genesis of this? It's not automatically it has came from heaven. There are 7 crystal system, or these are Bravell lattice, 14 Bravell lattice, or 7 Bravell lattice, or this like that. So there are a lot of things we know, but how? Whether this is correct or this is wrong. Something is written correctly, something is written wrongly here. But how to identify though whether really 7 crystal system is there or not? Whether Bravell lattice is 7 or 14 or 17, what is there? Okay, so how we can find? We can find with the words of X-ray diffraction. Earlier, this area, it is known as X-ray crystallography, or plane crystallography was there, which comprises of other things, but right now it's called X-ray crystallography. So if we go to the history, so there are a lot of researchers, they have made a list of, someone has made a list of 10 landmark experiments, someone has prepared 20, somebody has 25, somebody has prepared 50, or somebody has prepared 100 landmark experiments in 20th century, something like that, different numbers. But you will find X-ray crystallography in all of them, whether it is list of 10 experiment or whether it's list of 100 experiment, because X-ray crystallography has impacted the area of material science so much that you can find. So out of these 20, this one you can see all apart from this, but X-ray is there, which is in the top of that one. Okay. So before X-ray crystallography, let's say we are talking about 20th century, but before 20th century, this regular shape is not present. Yeah, it is present. If you see the snowflakes, or if you see some kind of churches and other things of earlier history, or some pattern of some dynasty or some civilization, you will find lot of symmetrical figures, lot of symmetrical things. But where it would have came, or some gemstones kind of thing is there, you will find, because these are occurring naturally in the nature. And people earlier also people are working on that. Earlier people are doing some research on that, but mainly through observing. Okay, there are symmetricity are there. So people have already got some idea or got some about regular shapes. And the first or the main thing has came because of the Kepler and Hooke's. They give postulates in 1750, and they start guessing. There is some building block, something like that, which is used and which are arranged so regularly, so that at the end you are getting some regular patterns. The building block idea at that time was they don't know what is that, but something. But now it has, at the end, with the advancement of science, with the advancement of research, experimentation, tools, technology, atoms can be find out. That's one. Okay. So you'll find all these kind of information, all this. If you are more interested to get, so micrography, a book is there. So where the origin of microscopic studies of the material was presented in. Okay. So the discovery of X-ray was such that it has not only given the name and fame to a lot of people, but established an area, established you can say a broad area of research where from on which material science has been established, or material science is standing on over that. So in 1895, it was discovered by William Röntgen, who got the first Nobel Prize of X-ray. This one. With first Nobel Prize in the area of X-ray. Okay. So another second one, Von Liu has used those X-rays, and he has discovered the wave nature of X-rays. He got with the wave nature, optical wave nature was there already established, and with that diffraction, grating and all thing was established. But here, what Von Liu has done, he has proven that X-ray is having wave nature, and on that basis, he started getting diffraction of crystals. So he got another Nobel Prize on the discovery of wave nature of X-ray. That and he has proposed two if postulates. Okay. Later on, Bragg's father and son group was there. W.H. Bragg and W.L. Bragg. They used that X-ray and the postulate what Von Liu has given, and they started solving the structure of different materials. And here they have solved a series of materials on the basis of position of diffraction spot and intensity of diffraction spot. So they got the arrangement of those things. So another Nobel Prize was given to them. So all these lot of Nobel Prize has been given for that. So what X-ray used of X-ray by Von Liu to give law postulates. What was that is the major, you can say, a major breakthrough in the area of he has given two postulates, because based on the optical or you can say light rays and light studies, he said if crystals are periodic arrangement, first if, and if X-rays are wave, second if. So if both conditions are satisfied, then the crystal will act as a 3-day diffraction grating for X-ray, similar to that of gratings, glass grating for that of optical light. So this condition you will get diffraction only if both the conditions are satisfied. And based on this thing, he used X-ray for a crystal, and he got this diffraction pattern. Diffraction means you get a direct beam and you will get a diffracted or reflect something like deviated weave kind of thing. So this is the first diffraction pattern Von Liu has got. But after getting this, what he has shown, okay, my 2if has been already satisfied. Otherwise, I would have got a straight beam, direct beam of that one. But here beam is getting diffracted. So with this pattern, he has solved two things. Yes, my X-rays are having a wave nature and crystal is having a periodic arrangement. Okay, any crystal is having a very periodic arrangement or okay. So with the advancement of science and technology, instrumentation, other things, now we are getting diffraction pattern like this, symmetric diffraction pattern. But this is the first diffraction pattern. This is the first diffraction pattern Von Liu has observed. Okay. So two results with a single experiment. So that was the greatest discovery of the 20th century. Okay. So X-ray diffraction means diffraction is having some peak and peak position and intensity. Both will give a information about two different things. Peak position will give about information about lattice, and peak intensity will give you information about atomic position. That is called a motif. And on combining these two, you'll get a crystal structure. So if I want to understand what is diffraction, so let's understand a very simple thing. There is an incident beam and there is some sample, some crystal is there on to it, and a beam is incidenting at a certain angle. So if so ideally what you are expecting, if it is you will get some kind of transmitted beam and some kind of diffracted beam if diffraction is happening. Otherwise either it will block or it will transmit it. Okay, so we are saying, okay, the transmitted beam is there, but diffracted beam is there in the some direction, and it is not restricted to any one direction. It is there. It may be depending upon the angle of incidence. It will be there for different directions. Okay, so if I'll so that is a very broad thing. Now, if we'll come to a crystal structure where there is a regular arrangement of atom or regular arrangement of unit cell or whatever you can say, basic unit. So if X-ray is incidenting on some crystal points or some atoms, so it will start diffracting and diffracting in all the sides. So so it will not be there for only one atom, it will be there for all atoms. So it will start. So if you consider a certain angle or particular direction, so all will get merged and it will get a superimposed beam in that direction. Okay. Now, what is those conditions? Okay. So we can see it any particular direction. Okay. We are not right now. We have taken this direction, but you can take any direction. So if there is a beam of incidence and there is a diffraction beam, so you can draw an imaginary line such that the diffraction beam will become a reflection. Why we are considering it reflection? Because we want to make our life simple, and we lot of laws of reflection is already been established, and we can make such that this imaginary plane will act as a planar surface where reflection has happened, and all laws of reflection now can be implemented. You are talking about this direction, I can talk about this direction also. Any direction I can take. So if direction I'm changing, then the planar change area will be easily, imaginary plane can be drawn out of that one. Okay, so this will make this will make our life easy, and this has been established by Bragg's. What Bragg is saying, for every diffracted beam there exists a set of crystal lattice planes, such that the diffracted beam appear to be spectacularly reflected from this set of planes. This is original Bloch's law, not 2D sine theta is a and lambda or 2D sine lambda. That is the Bragg's equation. Bragg law is this: for any or for every diffracted beam, there exists a set of crystal lattice planes such that the diffraction beam appear. It's not there, but it's appear to be spectrally reflected. This reflection has made life comfortable, and based on that, Bragg has established a mathematical equation that is called, you can say 2D sine theta, and based on that, I think you people have known this thing very well. Then he made another thing, 2D sine n lambda is or 2D sine theta. He has converted it to, that is the first order. Now he made it the nth order. So now, for making life comfortable, he has removed n from here. D by n he has made it. So instead of first form or first order, he has made it the nth order. Whichever order you will take, you will get a, according to lambda, will be there according to the plane. Based on these mathematical equations and based on these geometrical expressions, you can easily find that the spacing, how much it is, or you can find the lattice parameters. Okay, so these are the just mathematicals. Because of that reflection, he used all those reflection theories, reflection thing, and started solving this structure. So that was the general form. Now we shall see, if I am instancing an X-ray over a certain material, then I'll get a diffractogram. Now, by seeing the diffractogram, earlier it was like a photographic film was there, and the rings we are observing, that is called Debye ring. By seeing the rings pattern, you will find what kind of material is this one. If it is a very sharp spots, then you can say my material is a single crystal. The first identification you have to do, you can do with your material with X-ray diffraction, that whether I'm getting a sharp spot, okay, my material is highly crystalline and is a single crystal. If I am getting a rings out of that one, Debye rings, then my material is crystalline, but it is a polycrystalline material. And if it is a ring a certain angle only, then my crystal is oriented. If it is not, then you are getting proper rings. If it is oriented, then you get certain ring, and that too you can find there's a relation like 001, 004, 000, and family kind of relation, or 0 N0 family or N00 family, whatever thing is there. But by seeing the diffraction pattern, you can find it out. Okay, so this is the X-ray means you can say instrument diagrams or goinometer, where things are there. The parabolic geometry is there, lot of things is there. I think we can skip this. If anybody is interested, can ask this thing. So finally, if you'll get nowadays we are getting diffraction pattern like this, not a ring pattern, because ring pattern photographic cameras are there, but now we are using digital cameras, digital detectors, and all those things. So we are getting this pattern. So if my pattern is like this, or pattern may be like this, or maybe like this. So if my pattern is very broad, I can analyze, or I can conclude, yes, my material is an amorphous material, very broad. I cannot find my half width is very broad, or I cannot be able to find the half width at all of this one. If it is a crystalline, but fine nanocrystalline, then its peak width will be large. If it is a little bit higher crystalline, then this half width will decrease and you will get a little bit sharp. If it is very sharp, then it will be a single crystal, where half will be very difficult to find the half width of any of the peak. So this is the first information you will be able to get. But what are the other information you can get from an X-ray diffraction pattern? If I am having an X-ray diffraction pattern, I can see there will be some background and there will be reflection. So background will give you some other information, and reflection, with reflection you can find different information. If in the X-ray diffraction reflections, there will be an intensity of the pattern. So with the intensity, you can find crystal structure, atomic position, temperature factor, occupancy, and phase analysis also you can do it. From reflection profile, what kind of reflection profile you are having, then you can find the particle size, strain, whatever thing is there in the material. With position, peak positions in the 2D intensity profile. If you are having a position, and with position you can find the unit lattice parameter, what kind of symmetry it is having, what kind of space group you are having with the materials. With background, you can find what kind of scattering it is happening, because all different scattering will mainly contribute it to the background, whether it is Compton scattering, whether it is thermal diffusive scattering, or what kind of amorphous content it is having, or what kind of local disordering your material is containing. So with the one X-ray diffraction pattern, you can find lot of information in that. So that's why people are using the first experimental tool, first material scientist, what he do after synthesis is go for an X-ray, so that you will get some idea about the material, your physicity. So if I want to apply the X-ray diffraction technique in real-time problems, that is what I have discussed, what most about theories. But if I have to really imply what I am doing, how I can implement in my material, so how I can implement in my data or thing. So what normally people are doing, first thing is initial. Either you can do some initial characterization, or you can do a comparative study with standard data. That is the most commonly used. Or you can go for an advanced refinement, that is called Ritwell refinement or GSAR. Different software are there, but you can do structure refinement out of that one. Okay, so let's see, this is my X-ray diffraction pattern. So the first thing what I'll do, whether it is matching with this or matching with this or matching with this. So I can say, okay, regular pattern are there. My more or less is like this. So it's not a monoatomic gas, or not an amorphous, or not a nanoparticle, but it is a crystalline or powder particles. So first thing I do like this. So this is a real pattern of strontium titrate. The second thing, what I can do, I can take a X-ray diffraction pattern. I can take a standard directory, and I just see what are the position as per standard material, what is the position, what is the intensity. Then accordingly, I will assign the HKL value of that material. Okay, whether it's 22, okay, 22 it is there, but intensity is very small. But out of 32, the intensity is 999. That means highest peak. So this is the highest peak. So while comparing, we have to see a few things. You cannot randomly compare with the available directory. The first thing you have to see whether what kind of data it is having, whether it is here quality C is written, somewhere quality X is written, and somewhere it is deleted is also written. So you cannot compare with deleted one, because there might be a wrong thing, wrong report, and it has already been deleted. So you have to see for a recent one. If you are getting a star one, so that is the best quality, so better go with that one. Okay, you take that data, then compare. How you will do comparing? Compare the 2 theta and intensity both. don't compare blindly the two theta value. The peak, this data, peak position and peak intensity has to follow together. Okay. Let's say I am having peak at 22, peak at 39, peak at 46, but 32 I am not having. So it is not possible that this SRTI3, because 100% peak has to be there. The first peak which will appear is the 100% peak or the highest peak. Then the lowest intensity, lower intensity peak, and at the end, lowest intensity peak will come. Okay. So peak position and peak intensity, always you have to take care of that one. Okay. So there's the first part of the first thing, first conclusion of conclusion of the first part. Okay, X-ray diffraction is a fundamental yet essential tool in material science, and most material development study, it serves as a first characterization steps. I think everybody is you can accept it, or everybody is, and with that you can find the phase identification, phase purity, and find crystal size, crystal strain, defect analysis, or all you can find different. If you do some in situ experimentation, then structure evaluation, function correlation, all you can do it here. Okay, so this is the very basic. Till now we have done very basic things, everybody is used, but this is the first part. Now if time permits, we can go for second part. Okay, analysis using X-ray diffraction. Okay, so how we need analysis, what kind of analysis we can do. At the end I will show you some case studies also. So I can do ritual refinement. How ritual refinement? So this is the pattern what I have observed. Yes, I can assign some certain value, I can input certain information, and I can do the fitting. So what is fitting? Fitting is the least square data fitting, and based on that fitting, we'll prepare a model, develop a model, and that model will be based on the dispositions and intensity available with this fitting, and accordingly we'll get a difference peak. How much is your observed data and how much your theoretical data, and the lowest the difference, the highest quality is your data, or highest fitting, highest is the accuracy, high accurate data you will be getting out of that one. Okay, so this will be related to material properties, and all these values are very much related to material properties, and this can be done with different software. Somebody are using foolproof software, somebody is using GSAT software, somebody is using Write software, and all lot other softwares are already available. So I mainly I work with ritual refinement. So ritual refinement is done by a program which was developed by Ritualed, and I think it's developed something 40-50 years back. People are still using it, and this refinement program can be used not only for X-ray, for a neutron and other diffraction pattern also it can be used. What it will do, it will take it will do a least square fitting to a theoretical data to the profile data what you are using. Okay, so this was the first implemented. I told you more than 50 years back, something around 1967 and 69. It was first reported, and some manual calculation was done earlier. Later on, computer was used for that one. So what ritual refinement do? Ritual refinement refines user selected parameter. Understand? User selected parameters. The first thing is what you have to give a rough estimated parameter of that one. Okay, there you have to at least prepare a model so that and rough estimated near to it. It means you cannot fit a data of an elephant with the data of an, you can understand, with a cat. Okay, so you have to make a rough estimate of that one so that it will do fitting, and you will get a accurate value according to that. Okay. So ritual refinement refine the user selected parameter to minimize the difference between an experimental pattern and that is called the observed data, and the hypothesis made by the users, or a model based by the users along with the instrumented parameters, that is called a calculated pattern. Okay, so the question arises, can refine what it will refine, what it can. So it can refine the information about single crystal structure. It can improve the quality of the analysis because of the improved or accurate data you will be getting. You will get a refined lattice parameter, you will get a refined atomic positions, you will get a functional occupancy. So what does refined parameter means, or what does refined atomic position? Since we are giving, then what it will be refining? Okay. So there, what we are giving an approximate model. Let's say I am preparing a material, for example, barium titanate. Let's say barium titanate I am preparing. And now I am doping some X, Y, Z onto that. Some iron I have doped, or let's say some copper I have doped, or calcium I have doped. So now this system, the new system will not be a barium titrate system, it will be another system. If you see the diffraction pattern, you will get a little bit different diffraction pattern than from barium titrate. But you will see all are displaced, peak intensity may be varied, but on an average will look like similar to that one. Okay. The peak position may have shifted left or right, something like that, depend upon the material input, what you're giving. But peak position or peak difference or peak intensity ratio or peak, you can say, intensity decreasing or increasing pattern is almost similar. So the barium titrate data will act as a input one. And after putting some kind of doping, the exact fitting, the accurate fit, after getting accurate fitting, the parameter you are getting, you will get a refined parameter as per your new system. Okay, so the basic system that was a input parameter, and for a new system which is having similar kind of pattern, you will get a more accurate parameter and accurate position according to your modifications. So you will get information about materials, information about single crystallinity, information about phasicity, single phase is there. Or if you are having more than one phase, you can find that also. If you are having ratio of two phases, how much difference phase you are having, you can find that multi-phase or their ratio content of two different phases. That also you can find it out with the help of ritual refinement. So method of refinement means method of so it will refine the crystal structure. Okay. So crystal structure means atomic positions. It will give you very precisely. Let's say for an example like this. Here I have given example what kind of information you need for this one. So I need information something like that. What is my material is? What are how many atoms are there of so that it can form a pure unit cell, complete unit cell. Then what kind of space group it is following? What is an approximate parameters? What is an approximate Wyckoff position? Or Wyckoff position is a very standard thing. You can find it out uh, in this book of crystallography is there. So you can find it out on that. Okay, depending upon the space group, they are having standard Wyckoff position. Then you can find it out what it is having. So with the help of this thing, you can find diffraction pattern and you can define over that one. So you can find reflection positions. With that, you can find it, as I told you earlier, cell size, space, group symmetry, and all those things you can determine. And with intensity, you can find the atomic positions. Okay. So what does you need for a ritual refinement? If I have to do a ritual refinement, what input you want? I need the first thing and first and foremost thing is I need a good quality data. Data should be of a very good quality, which is having very low background, and it should not be taken in a very hurriedly so that all noise will come in that one. So a respectable good quality of the data you want. A structure model, just as I told you earlier, that makes a physical and chemical senses. And what does physical and chemical senses means? Okay, this is chemical senses कि it is has a proper structure, proper balanced structure. Physical senses means proper. This is having a Wyckoff position and space group. So this has a proper physical and chemical senses. A suitable peak and background function. You should be aware about what kind of peak you will be getting, what kind of peak profile you will be getting, what kind of peak positions you are expecting in this kind of X-ray diffraction pattern. Okay. So obtaining, so three, four things we need, but how to get, because the high quality experimental data, most of the time it is not in your hand, but you should follow certain steps so that you will get a good quality data. So while taking data, before that you just confirm whether the instrument has been aligned properly or not. The beam overflow is not there. The sample should not be very thin so that a thin specimen error should come. It should not be done in very hurriedly. Okay, a scan of around 100 degree in 5 minutes so that you will not get a good count. It should be done a little bit slow manner so that you will get a good count to diffraction intensity so that it can make a proper pattern out of that one. Sample transparency, sample roughness, and all those things you should take care. Then you will get a good quality X-ray data. Okay. Then you should describe the crystal, whatever preciseness you can give off. Okay. Space group, it should be accurate. Lattice parameter, it can be an approximate. Atomic positions are fixed. So as per space group, you can select the atomic positions, atomic site occupancy, what you have planned that you can give, and what are the thermal parameters approximate you can give, and the refinement program will take care of other things. Okay. So just an example, what are the requirements and how you are getting. Lab 6 experiment. So this is my chemical senses. It's a lab LAB6. The chemical formula of this system. It has the physical senses what the system is having. The space group is PM3M, PM bar 3M, which is having a 221 number of space group, and out of that P221 I can find the Wyckoff position, what 1A with or 6F it is there, and this is my lattice parameter. So this is the physical parameters what I have here. So this is lab 6. So you can say 1A and 6F, you can reflect the 6 time of thing is there, it can be considered. Okay. So these are the standard positions. There are some positions which are little bit variable, just like this. These are fixed positions, 0, 0, 0, 0 0.5, 0 0.5, 0 0.25, something like that. But this number, you will see some alteration numbers there. So it is having a relaxation, means it's something plus minus, you can do it here so that it can adjust the crystal structure. So those things you should be able to understand. Okay. And this kind of information you can get lot other places, not only in the book of International Book of Crystallography, but from some lot of websites are there, databases are there. With that you can use and you can do the calculations. So these are some parameters which you should take care. If anybody is interested, they can discuss, and I can tell you what are the parameters, where it is placed, and how you have to do the refinement. So these are the some formulas it will be used. But for a refinement, there's a strategy you have to use ritual refinement. It started with what you have to do it first, what you have to do it second, that everything is given. And if you follow that strategy, you will not stuck into a potential or false minima. Ultimate aim is to get a minima so that fitting will be overlapping properly. But if if you not follow a strategy, it means strategy based on experiment based, people have done a lot of experiments, lot of fittings, and they have made a recipe out of that one. If you follow, then you will having a less chance of stucking or getting at a wrong place or ending up in a wrong refitting, minimum divergence. Okay. So you refine all those things. So what is that strategy? The first thing is you have to do a fitting of scale parameter, then zero shift parameter, background, then lattice parameter fitting. These are the parameters reflected in the file. If I'll show you, these all paragraphs are there in that one. You can find this thing is YouTube also. So this is the software where you can find it out. Let's say these examples are there. These are Wyckoff position examples, and this is the file what you are getting. What I told you a strategy, what you have to do a zero background fitting. This is a zero parameter. This is the scale parameters. These are the backgrounds. These are the background coefficient, how much these are there. This is the space group. This is number of atoms, how much is there in that cell. This is the chemical formula. These are the Wyckoff positions. Here you have to put it like this. So you can put thermal parameter. V overall is the thermal parameter, peak shape parameter, lattice parameter. All things are there. If you read it carefully, then you will understand all these things very clearly, and you will be able to understand what value has to be given. These are the value which are related to certain instrument and certain conditions or certain experiments. So here we should not, you can say we should not deviate all these things, because for X-ray, there's a certain code is there. So every time you are doing X-ray, so you have to use those code. You cannot vary from 1 to 1.1 or 1 to 2. Okay, number of parameters, number of phases, that thing is there standard. What you wanted output, you want HKL values or you don't want, so that is there. So these are the instrumental para or setting parameters, which we rarely touch. But if you're going for different set of experiments, then only we touch. Okay, with this software you can do, and we are getting this kind of refinement patterns. Okay, this software is freely available. That's why most of the people use this one. If anybody is interested, they can see and they can download it from this page, foolproof suite pages. And this is the latest link, or they updates is very frequently. After every 2 3 years, they used to update it if any new version is coming, something like that. So after installation, you will get this kind of window, and after opening this window, this next window will come, and this is the place from where software will. Apart from this, right now this foolproof is hosting lot other software also. So if people are understanding, they can use different software also. But for ritual refinement, you can use this file, and with this you can prepare the input file of your ritual refinement pattern with this EDPCR. Either you can edit it or you can prepare it. Okay, so this window tool is there. If you open it, you can plot it, you can do all those things are there. You can edit PCR. PCR means input file. You can edit EDPCR means edit PCR. With this, you can edit, or you can run with PF, and you can even if simple plotting also you can do it from here. Like this, we are doing it, and we are getting a pattern like this. Okay. So this is more about X-ray diffraction. This is the file you will get, and here you can give all the input parameters. What I saw with the strategy or everything, you can set it here. Okay. Now I'll come to my case study. In a bit, just I told you an experiment of barium titanate. If I'm doping in hafnium, what is exactly happening with X-ray? How I can confirm my hafnium is going inside or not? So what I have done hafnium doping or hafnium replacement in place of titanium or at a different. So you say BHT 0 means hafnium is 0. BHT 5 means hafnium is 5%, 8%, 10%, 15, 20, 22, 23 to 40, 40. So systematically I am increasing the hafnium content. Okay. So what I am getting almost similar pattern to that one. Crude way, it's almost similar pattern. But when I am seeing very closely, what I am seeing, there is a systematic shift of diffraction pattern from right side to the left side. Means I can say from higher to theta to lower theta. The first thing is, okay, I am doing I am doping systematically, shifty, systematic. So the first thing is, yes, there is a possibility it is going, or I can say, yeah, it is going. But whether it is going properly, how I can say? Now, second thing is what I can see is 2 theta wise, 2 theta scale wise, it is going from right side to left side, means 2 theta value is decreasing. If you see, if 2t sine theta is equal to lambda, these are equal. So d and theta is inversely proportional. So if theta is decreasing, d or d spacing is increasing. So that means hafnium is increasing the d spacing of system. D spacing means the unit cell volume is increasing. Why it will increase? Because ionic radius of hafnium is bigger than titanium. So when you are removing titanium and putting hafnium, so you are removing a smaller size in atom and inserting a bigger size. So it will expand your unit cell. So that's why your D spacing is increasing. So second analysis I have done, because of the higher ionic radius replacement, my peak is shifting systematically to left side. So this is strongly proving my material or hafnium is inserting into titanium matrix. After refinement, all those parameters, what I have seen, okay, at certain composition, this one parameter is refined well, and after certain composition, this different slope it is refining well. So what does it mean? It means there is a change of the structure. Okay, from a tetragonal to cubic, it has been changed. Okay, so there is a second thing what I have observed, there is a change of crystal structure after certain amount of doping. So what are those things? That also we can find it out here. And the third thing what I have observed, to more conformly or more boldly what I have given, what I have raised the observation earlier. So see, you can see with the lower 1, 0, there I have get a 1, 2, 3 peak, and this peak, especially this peak, you can see it's coming close to this peak and merging with that one. After certain, this one notch is there, very small notch there, but from here that notch is almost disappeared. So similarly to here also you can see this notch. So this indicates the change of crystal structure at certain composition, and that change very slowly. Okay. So with this, you can find it out at what composition. If I'll fit with this barium titanate at room temperature is tetragonal. So first what I have done, I have fitted all, even though crystal structure has been changed up to 30%, but what I did, I fitted with all with a tetragonal. And after certain composition, I see these ABC parameters are moving parallelly. So there is no deviation. So what does it mean? It means here it has been merged and it has been formed a cubic system. So you can find it out at what composition level my system is changing, something around 12%. My system has been changed from tetragonal to a cubic structure. So this is the modified lattice parameter diagram. You can see at what place, and this is already this data is already expected and is matching well with the lattice parameter observations. Okay, so similarly, different doping, all those things we can do it here. So this is all about my and using X-ray diffraction for basic experimentation. So these are the acknowledgement what I there for who will help me for doing this kind of work, whether it's Director CSIMT who helped in providing all those infrastructure facilities and giving funding for the research. Apart from CSIMT, CSIR is also giving a lot of funds. Other funding agencies with whom we are working, and the team of PhD scholars what we are having. So now the session is open for question answer. If anybody is having any question, we can discuss. Ashish ji, any question from anybody? Anybody has written any question?
Sir, till now nobody has responded. No, one question is there.
Please.
Sir, how to assign peak to different elements?
How?
How to assign peaks to different elements?
Different element for X-ray, it's nothing called different element. It's a unit cell. Unit cell like barium titanate. This is not related to barium or titanium or oxygen. It's a barium titanate. It's a complete unit cell. Okay. So if you are having a barium titanate, first thing we have to clarify whether my material is barium titanate or it's a composite of barium and titanium. Okay. If it is a barium titanate, then you will get an individual peak of barium, titanium. Oxygen, normally it won't come. Okay. Because oxygen balancing and diffraction or getting oxygen is little bit difficult. So barium titanate composition is there, which is having individual identity, or when they have left their identity of formed a barium titanate crystal structure. So if you have barium titanate crystal structure, then there is a single identity of barium titanate. But if it is a composite, then you will get a different peak of barium titanate. So you can, the first, as I told you earlier, either you can do a JCP-DS comparison, or you can do a refinement of two phase, barium phase and titanium phase, and fit it. So you will get a two different profile, one with respect to barium and another one with respect to titanium.
Hello. Good afternoon, sir.
Question is how we can quantify the component in multi-component system?
Multi-component like this. Let's say I have two component barium and titanium. So I'm doing a refinement, and there in the refinement we are getting how much content, because I started with 50-50, let's say 50% barium, but it may not be at the end product, maybe 50-50, because that was my expectation, that was my initial I can say arrangement. But at the end we'll do a lot of processing, maybe heating, maybe pressure thing, maybe. So there might be loss of some material, or maybe because of temperature some are volatile, it may evaporate. At the end you may get some other different thing. So we'll do we used to do diffraction, we take diffraction pattern of two material, two phase, we do two phase refinement, and based on the intensity profile pattern of two and the comparative or the ratio between these two, we can calculate the percentage of individual phases. And ritual refinement will do it automatically. Either you can do it manually or you can do it automatically with the help of software, ritual refinement software. With one ritual refinement software, you will get lot other informations. Not only phase one, phase two, accurate lattice parameter, peak profile, or accurate Wyckoff position of the unit atom in the unit cell, but you can get the phase amount, how much occupancy it is having, how much loss it is there. That can be taken out from a single software.
Jyoti NJ is also asking if XRD contain our substrate peak, how to remove them from our data. Maybe he's talking about how to use the software to remove the
Yeah, a lot of software are there which we can easily do it. Remove background software kind of thing is there. If you want to do it manually, you can take a diffraction pattern without sample and one with sample. And those people who are not having access of software, they simply subtract those things. But the condition is that both experiment has to be done in same environment with same parameters.
And Nirbhay sir is also want to ask some
please.
question.
Dr. Nirbhay, please.
Dr. Nirbhay sir.
Yes, sir. Thank you, sir, for nice talk, sir. I have, sir, few questions. Those are probably also related to the same thing. One question is, sir, what are the precautions while doing the ritual refinement for the composites? Means if the pure compound is there, then it is easier always to do the ritual refinement. But in general, this is question related to early researchers or master students. Those are doing the X-ray diffraction analysis. So what are the basic precautions which we need to consider while doing the ritual refinement?
Okay. See, there are, you have asked one question in two ways. What
Yes,
are
sir.
the precautions you have to take in ritual refinement? And the second one is what are the precautions you have to take in doing ritual refinement of a composites when you are having more than one phases. Okay.
Yes, sir.
So
Yes.
for doing in general, I'm trying to explain you in general. For doing ritual refinement of any material, the first thing you should follow the strategy what I had given. I have shown you earlier. Okay.
Yes,
So
sir. Yes.
these are the things you have to follow. Refinement strategy. What first you have to refine, then how you have to refine, which one first, which one second, which one third, which one fourth. And second thing is while refinement, if you are making a file like this, I'll
Yes,
just you are able to see this file.
No, sir.
No, sir.
We are not able, sir. You can share because
Okay, it's unshared. Okay, I'll just share it again. Share screen, share. Okay, now you can see this one.
yes, sir. It is
Okay.
visible.
Yes, sir. Yes.
So this is the file. As I told you, this strategy you have to follow. And second thing, see this RAT, RAN, RPR, RGL. Okay. So these are the relaxation parameter, atomic relaxation parameter, anisotropy, all those things are there. So if you are a very new beginner, this number should be or if not new beginner also, if you are at the initial stage of fitting, so this number should be minimum. So
Yes.
that you just like that, if for a blind person, if you want to try to walk, you just trying to tell him to walk in a very small steps rather than start running from that direction. Okay, so these are the small steps. Okay, after following the strategy and with the small step and using the proper parameter input, if you are having properly, then you will slowly you will get a proper fitting out of that one. Okay,
Yes.
if it is a matter of composite, follow the same thing, but for a one time, first time you fit a single phase of A phase, another
Yes,
time
sir.
you fit for a B phase, then merge it for a AB phase. Okay, so don't start with AB together because then for a one material you are having 18 parameter to refine. For another material you may have around 30 parameter. Two, three
Yes, sir.
parameter will be common, but most 30 parameter. And deviating in any of the parameter will reflect in your larger deviation of your diffraction pattern.
Yes.
Okay, so better try to fit phase one at one time then phase 2, only phase 2 at another time, then multi and do fitting of both together, phase 1 and phase 2. But follow the same strategy.
Okay, sir. And sir, one request is also from participant side. They basically want the PPT or PDF of the presentation. So can you please provide the same, sir?
What I am unable. Can you repeat? I'm unable to.
Okay, sir. Sir, basically participant want the PDF or PPT of
Okay,
the
okay, yeah. I can share with the organizer, and
Yes,
I think
sir.
organizer can recirculate it.
Yes, sir. Yes, sir. So these are the two questions from my side, and now it is open to all participants. If they want to ask anything regarding the talk, they can either write in a chat box or they can directly ask. I will unmute.
So there is a question from Shrivin Singh. If the spacing between atom is more than 50 nanometer, can we use X-ray to get patterns?
Spacing between atoms, then it will not be a unit cell. There is no crystal, you can say, lattice arrangement. It will not form a lattice. Okay. For let's say if you have prepared a very big lattice of 15 nanometer, anyhow you have prepared. Ideally it is not possible, but let's say if you have prepared, then the spacing is 15 nanometer. Then accordingly you have to select a ray which will not fall X-ray, but suitable to that wavelength. Then you will get a diffraction pattern, not with X-ray.
Sir, there is one more question from Sumanika Srivastav. She's a biotechnology BSc student 5th sem, and she want to know what is the relation between Miller indices and XRD.
Miller indices and XRD. So Miller indices, if I'll say, let's say consider a unit cell. Unit cell means as I shown you earlier. So this is a unit cell kind of thing. If nowhere else is there, no. Okay. So this is a unit cell. So you can forget about other things, but you just see a cubic unit cell like this. So these are an imaginary plane. Just like if I'll say a die, if I'll take a dice, it has a plane. All six sides there's a plane. Okay. So if all those are imaginary plane, ideally these are only ball kind of thing is there. I can consider these two ball as a, if I make a line of that, then this is a plane, single line. If I'll take a four line and if I'll make up like this, these are the plane. So this is the imaginary plane. These are so close so that they are attached to each other, almost attached to each other. If I'll have a pattern of this one, I'll show you. Okay. So you see, ideally crystal structure is like this. And these are some imaginary planes. Eh, When these planes can be found with the help of X-ray diffraction, because plane, when beam of light is falling, in front of any plane, if beam of light is falling, depending upon the reflection, it will reflect, and accordingly you can find it out the which pattern or which plane it is reflecting. Okay, so this X-ray is used for finding those planes, and those planes are represented in the form of Miller indices. So these are the relation. Miller indices can be found with the help of X-rays, X-ray reflections only.
Okay. So the Sumanika Srivastava also want to know where to find this JSPDS software.
All X-ray instrument has JCPDS directory in that one. So from wherever you are taking X-ray diffraction, just tell those operator, tell those instrument person. So which JCPDS data you are having. Most of the time it is inbuilt in the systems. But there are American Mineralogist Societies also there, which also has lot of that is freely available. and that is also have lot of JCPDS, means lot of directory or lot of reference data in their file also. But
There is one
all
more.
instrument has, all instrument has.
There is one more question from Balwant Singh Labana.
Hmm.
If the sample is amorphous in nature, so how XRD will be useful? Or we can get any data from XRD, how to reiterate if we are capable to use the XRD for the amorphous material, sir.
See, if it is if you are having material amorphous, amorphous means there is no regular arrangement or
Arrangement.
no regular ordering of your atoms. Like this, there is no regular arrangements. Okay. If you are having an amorphous material, if you take like glass, if you take X-ray of a glass, you will not get anything. You will not get anything doesn't mean nothing. That also says you will get a broad background out there. Okay. So with broad background in X-ray diffraction pattern, you can tell that material is amorphous. And just like for a crystalline material, there is software called reticle refinement. There is for amorphous material, there are a lot other software which use those background information. That is called background. Amorphous means you will get a broad background out there. So there are a lot of software which use those background data, and you will get what kind of scattering, what kind of if ordering is very low, single that also is there. Those things can be got it from there. Directly, we are not dealing with amorphous, but yeah, there are a lot of people are there which are working on amorphous material, and you will get from those software only.
Mangalam Soni is having a question. Actually, it's a request. It's a request to you. Please tell us the software again so that I can take a snap of it. I think he is asking for foolproof
Yes.
software.
Just you write foolproof, and then this site will come, and from there you can download. There are versions, the latest version you can download as per your desktop or as per your either Windows or Mac, whatever you are, Linux, whatever you are using, you can download software. So you can take this. Just Google it, you will get it.
Can you please share the open source software? This is open source.
This is open source
This
only.
is open source.
Yeah,
Okay.
this is the link. This is the website. If you can type it here and you can just search it. So directly it will open this page only.
Okay. I hope participants' question has been answered. So I am also having a question for you, sir.
Please.
I am working in the field of magnetorheological dampers, where we are using this carbonyl iron, which is ferroelectric in nature.
Okay.
So I am having an issue. Are we manufacturing this carbonyl iron in your lab or somewhere?
No, right now, no. I am also working on ferroelectric materials,
Yes.
but not of that type. My
Okay.
material is mainly barium, BZT based materials. There we are doing ferroelectric measurement with the help of this PE hysteresis loop analyzer, but not with X-rays and other things.
Sir, there is one more very specific question from Muskan Sharma also. She is asking, in my research paper, I have plotted XRD graph in origin, but for WH plot, I have used full proof as R square value was not appropriately by linear fit in origin. Should I plot XRD graph, made it in full proof, but chi square value is 2.6?
See, this the chi-square value of 2.5, 2.6, it doesn't matter much. Okay. What you have to do, you have to compare your profile, because that chi-square value of 2.4, 2.5, 2.6 more or less depend upon lot other parameters, not only with the fitting. If your background is not properly fitting, which is not the part of your sample, then also it will increase. If you are having thermal parameter, which is not the part of your crystal structure, that also will increase. Okay, so you have to see the profile. You have to see the profile, how it is fitting. If I'll show you some profile fitting. Okay, if your pattern is how pattern you are you have to see this, how it is properly, it is fitting very well. If it is not, then it is not appropriate. If it is fitting well, then any chi-square value is acceptable.
And I think this is the last question and very basic question, but she is asking, what is the purpose of using monochromatic X-ray in XRD?
Uh, Monochromatic, so lambda, what you need to Bragg says, log says 2d sine theta lambda. Okay, if you are using white background, means if you are
White
not
light.
using monochromatic, or if you are using X-ray of lot other value, lot other lambdas or lambda with delta lambda, then for any peak you will get, for any one plane you will get lot different peaks. Okay, d for lambda 1, d is constant. D with lambda 1, D with lambda 2, D with lambda 3, D with lambda 4, then you will get a variety of peaks. If your peak position is not very different, then you will get a very broad peak out of that one. The width or the lambda delta is there, same lambda will be reflected in your D values. Then you cannot say your material is a single crystalline or nanocrystalline, because the end diffraction pattern will give you a very broad peak, because lambda is having a range of wavelength. So the peak which is like this here, it will become like this bigger one. Okay, so you can say for finding crystal you need a very unique single crystal, so that you will get ultimately what you need a 2 theta value. 2 theta means a peak position, peak accurate. More accurate value will we get at the 2 theta scale or x-axis, the more accurate data or analysis you will be able to find in terms of your lattice parameter, crystal structure, and other things. Am I clear?
Yes, yes, sir.
Sir, one more question from chat box. One student is asking why ritual refinement of carbon material is challenging.
Ritual refinement of
Carbon material or carbonaceous material is challenging.
See, low, not only carbon, but low Z material, because low Z material, you can say they're more contributing to our backgrounds. Low Z,
Yes.
EDEX is very low. Doing a EDEX is very challenging. Doing ritual refinement is very challenging. Means any low Z material, because it is very difficult to differentiate between nearby atoms. It is very difficult to differentiate their positions. So always it is challenging because of their low Z values. Higher Z, then scattering factor will be very high. Then you will get a very good proper peak. The scattering factor with respect to Z, if you will see, then with respect to Z, yeah, if you will see, then it is very low at with low Z value.
Yes, sir.
More atoms, more electrons, more electron cloud, more diffraction you will get. So you will get a proper information. Here, diffusive information is more.
Yes, sir. So when sir you were talking about the scattering factor, then it is atomic scattering as well as electronic scattering factor, no?
Yeah, scattering means all scattering. Right now, all kind of scattering depend upon electron cloud. So scattering means if overall scattering is less, so everything will be less.
So intensity should be less. That's simple.
Yes.
Okay, sir. And sir, one more question is, why do graphite peaks appear very sharp and intense? This is question from a student.
Why do graphite
Peak appear very sharp and intense? So basically, I think this answer should be we are getting more scattering, no?
Yeah. Is that? See, if it is a carbon and graphite is a 2D long layer.
Yes,
Okay.
sir.
And when you are talking about carbon atoms, then it will be a very small area, or you can say confinement of a few unit cells or grains. So if it is graphite is almost a single layer material of or a single crystalline layer. So ultimately it is overall it is contributing small it is contributing to a bigger one, and that too small contribution coherently. All because layer 2D layer is their bigger layer, and all are giving signal, but small signal, but coherently together in a single direction. So we are getting.
Yes, sir. One more, sir, question. If you have time, I can ask two questions are there. One is, can I ask, sir?
Yeah, please.
Sir, how do you model stacking faults in a layered carbon using reticle refinement? Stacking faults पूछना चाह रहे हैं layered carbon material में
Stacking
कैसे हम?
fault, I think ritual refinement say it's difficult. Normally, we used to get it from TEMs.
Yes, sir. Yes, sir. So this technique is not good if we want to.
Yeah, it's technical.
Okay. And one more question is, sir.
Yeah.
Why is the graphite 002 peak often fitted with a Vigot TCH function rather than pure Gaussian or Lorentzian? This is, sir, I think this is a material related question and we can skip this because this is so technical and without seeing the data we cannot answer this.
Yeah,
So,
I'm unable to understand the question also. Which
yes, sir,
once I'll see the data, then only I can comment on that one.
Exactly, sir. Question was, sir, basically why is the graphite 002 peak often fitted with the Vigot or TCH function rather than pure Gaussian or Lorentzian function?
Yeah. So we see for normal cases, for normal X-ray, pseudo-Vigot is the pseudo-Vigot means Gaussian plus Lorentzian is the one combination of these two is the one which is there. But for some material specific, because of certain kind of modification structure, then depending upon the connection. Hello.
Yes, sir. Yes, sir.
Yeah.
We are
Yeah, depending upon the conditions or processing condition, their structure get modified, है ना? And then accordingly peaks will get modified. Then we used to fit it, but that is a very condition or material specific. In general, pseudo-Vigot is there.
Yes, sir.
For X-ray, for a strain-free material, standard material, properly polycrystalline material, pseudo-Vigot is the one which is normally used for fitting of these kind of patterns.
Yes, sir. Thank you, sir. These are the questions from participant side, and now I will also request to organizing team member, if you have any question, you can also ask to sir. There is a no question, and
Sahil sir, very excellent presentation given by you. That is a very learning process. So if students will to avail facility of your lab, how they can avail, sir?
In any of the CSI lab, if you want to visit, there are a lot of other programs are there. Then Jigyasa is the one through which students are visiting regularly to any of the CSI institute, not only in my institute, but to any of the institute. So in every lab, there is a coordinator called Jigyasa coordinator, and mainly that is for students and college-going students, mainly for school students and college-going students. And sometimes faculties are also coming through that. If they want to visit, they want to see the institute, what kind of work it's doing, they can interact with them also. So Jigyasa is the one, and otherwise directly people can come and interact also. But if you are coming in a group, then better to come with Jigyasa because they do a lot of arrangement also. Okay, visiting arrangement. If you want to miss, if they are visiting for a full day, then different labs, somebody they keep for instructing and what kind of thing is their food arrangement. They used to do all those things there.
Is there any specific time for this particular Jigyasa? Or?
No, it's round the year, but 2-3 times in a month.
Okay.
So whichever slot you will be getting.
Okay. For this, we just
and every lab, every research CSIR lab, I'm talking about CSIR lab. Every CSIR lab is having their foundation day, and that foundation day is open for all.
Okay.
Okay.
I think
So in that
recently
foundation day, there is no permission, nothing. You can go and directly visit.
Okay. Perfect. MIT group was also having the MOU with CSIR also, sir.
Yeah, very good. So you will be, you might be aware about all those things. You can visit, send the students or your nearby laboratory, whatever it is there, Bhopal or in Delhi. You can send students for a regular visit over there, for a 1-day visit or for a 2-day visit, something like that.
Okay, sir. Thank you very much, sir, for your.
Thank you.
Thank you, sir. I would like to again thank you for a wonderful and insightful presentation. And you handle every question with a great sincerity and very well taken. Thank you for your efforts, sir. Thank you for valuable time.
Thank you. Thank you very much. So I'm leaving.
Yes,
sir.
thank you. Yes, sir, you can leave. Thank you.
Professor, I am on call with Dheeraj sir. Dheeraj sir को please के अंदर आने में दिक्कत हो रही है.
Dheeraj Singh is there, sir. Dr. Singh is there.
Ma'am, he joined, ma'am.
So, we have now reached to the third session of the national workshop, Advanced Characterization Tool and Techniques for Material Science and Engineering. To formally begin the session, before inviting our distinguished speaker, Dr. Dheeraj Singh, sir, may I have privilege to introduce him to the gathering? Dr. Dheeraj Singh is currently serving as an associate professor in the Department of Physics and Astrophysics, University of Delhi. He completed his PhD in physics from Banaras University in 2010 and pursued distinguished postdoctoral research at NCL Pune CSR Nehru PDF, South Korea, and University of Bremen, Germany. Prior to the joining University of Delhi, he held faculty position at IIT RAM, Ahmedabad, and the Central University of Gujarat. Dr. Singh is the recipient of several prestigious awards, including Alexander von Humboldt Fellowship, Germany, JSPS Fellowship, Japan, and Dr. D.S. Kothari Postdoctoral Fellowship, and UGC RFSMS, Japan Fellowship. His research interests include functional nanomaterials, solar energy materials, spectroscopy, ionic liquid, biomolecular interaction, and DFT calculation. He has successfully completed major funded projects under SERV DST, DST Inspire, UGC CSR, and IOE scheme. With over 103 international publications, 5 books published with Springer, 9 book chapters, and 2 granted patents, USA and India both. Dr. Singh has made notable contribution to the material science and spectroscopy. He has guided 7 PhD scholars, delivered numerous invited talks, served on academic boards, and reviewed more than 120 research manuscripts for reputed international journals. Please, sir.
इसमें आता है नहीं ये मुझे नहीं पता ये वाला है इसका मुझे आवाज इसका भी आ रहा है Am I hearable?
Yes, sir. You are audible and visible, sir.
Okay. Thank you. Thank you, sir, for nice introduction.
Welcome, sir.
So now I am sharing the screen. My screen is visible?
Yes, sir. Yes, PPT is visible, sir.
Thank you, sir, for nice introduction. So today, first of all, I would like to thank the organizer, especially Professor Manisha ji, Mishra ji, and also Dr. Ashish ji for invited me to deliver the talk on this very specific workshop. So today I am going to deliver a talk on Raman spectroscopy. I will start from very beginning fundamental principle and their application for materials characterization. So I hope there are some PhD students, research scholars or beginners. That's why I will explain from very beginning of Raman effect. So as Professor Ashish ji explained, I am associate professor at University of Delhi in Department of Physics, and this is my contact details. If anybody wish to contact me for any query, most welcome. So I have divided my presentation in these 5 distinct points. First of all, I would like to describe about saga of Raman spectroscopy. What is so special about Raman effect? Why Raman effect are so impressive for materials characterization? And how we can explain Raman effect by classical theory, and why classical physics is failed to explain the Raman effect. And what is the role of quantum physics and quantum theory to explain Raman effect by explaining the relative intensity of Stokes and anti-Stokes line. And I will explain how one can analyze the Raman data of any particular material using Raman features. Actually, Raman spectroscopy give information from 3 different parameters: frequency or wave number shape, line width, that is full width hot maxima, and third one is relative intensity. So any materials can be characterized on these 3 basic parameters. I will explain how these 3 parameters are important. After that, after discovery of Raman effect in 1928, now more than 28 variants of Raman spectroscopy has been developed. Now a lot of instruments are particular materials characterization in different field has been developed. Many Raman spectroscopy technique, resonance Raman. Now using the nanotechnology with Raman spectroscopy known as surface enhanced Raman scattering technique. Now using the STM technology, the same working principle is tip enhancement Raman effect and non-linear Raman effect like coherent anti-Stokes for fast dynamic and ultra-fast dynamic effect. So every research area, what types of research area you are choosing, so more than 28 variants of Raman spectroscopy has been developed. So few of them I will explain today in my talk. In last, I will explain the application of Raman spectroscopy for materials characterization. For this, since Raman is a non-invasive and non-destructive technique for tool real-time monitoring, I will show the application of Raman spectroscopy in simple molecular interactions. How we can predict the hydrogen bond or interaction between 2 molecules, especially from lower molecule or smaller molecule to larger molecule in DNA and proteins, and what is the role of Raman spectroscopy in carbon-based nanoscience, like carbon-based material, carbon nanotube, graphene, fullerene, and quantum dot. How the Raman spectroscopy are very important. Further, I will also show the surface enhanced Raman scattering in the presence of nanomaterial. How we can sense the single molecule detection, or we can sense the coronavirus, or how we can sense the particular cancerous cell using the nanotechnology and Raman effect. So this is my outline of the talk. And very beginning, I would like to explain what happens when light falls on a molecule. When electromagnetic radiation falls on a molecule, then what happens if your light is fluorescence, or we give luminescence, we call it fluorescence spectroscopy. If your light is scattered from your molecules, then we call it, I will take the pointer options here, laser pointer. Okay. Now, if your light is scattered from your molecule, then we call it elastic or inelastic scattering. Actually, Raman is a inelastic scattering of light from a molecules and material. Means any light which are inelastically scattered and giving the information about their structural things, then we call it Raman effect. So now if your light is absorbed by your molecule, we call it absorption spectroscopy. If your light is transmitted through the sample, we call it transmission. And today I am interested only in Raman effect, which means that your electromagnetic radiation incident on your surface can be scattered inelastically. So now this is the basic electromagnetic spectrum. This is, I think every student should know about that. Electromagnetic is actually types of spectroscopy can be defined by this electromagnetic radiation spectrum. Now what happens if you are using a radio wave frequency in this region of 10⁻³ to 10⁻⁻1 centimeter inverse, or in terms of wavelength 110 to power 1 to 10⁻⁻1 meter wavelength, then we can see that if incident on radio wave material, then it gives the information about the spin orientation in magnetic field, and the technique based on this system is known as NMR, nuclear magnetic resonance. And now if you are using the light, incident light in this region, that is known as electron spin resonance. That is, means if you are applying the microwave light in any molecular system, it will give the information about the molecular rotation, and it falls in the category of this region. But now when you apply the near infrared area, you can see that this frequency region light, if you are incident on your material, it giving the molecular vibration, and every molecule have vibration and picosecond level. If you are applying any IR light, mid IR light, then you can find out it will absorb by the molecular. So generally IR and Raman both give the similar information about the molecular vibration. So you can see that the IR region can be also categorized in three categories: far IR, mid IR, and near IR. So generally, this mid IR Raman spectroscopy falls in this mid IR region. So now there are certain difference between Raman and IR. I will explain after giving the example of Raman spectroscopy. Then we can see that UV light. When valence electron excitation is there, UV light will be there, UV visible absorption. If you are applying X-ray light on your molecular system, then inner electron excitation will be there. Now X-ray techniques are used. Like XPS, X-ray photoelectron spectroscopy, generally developed on this. So you can see every technique has been developed, instrument has been developed when we are applying types of electromagnetic radiation in that particular region, and we are getting particular information in that particular region. Like for nuclear motion, nuclear excitation, if you apply the gamma radiation, now you can see the gamma spectroscopy will be. So today I am going to define this Raman spectroscopy, which are giving information about the molecular vibrations and in terms of spectra. You know that every molecule have some molecule vibration. Now vibrations can be 3n minus 5 or 3n minus 6 number of vibrations. When we applied any visible light, then what happens? In IR case, if we are only apply the infrared light will be absorbed by the molecular vibration and give the IR spectra, IRP. And since every molecular vibration have different frequency, according to mu is equal to 1/2 pi under root k by mu, it means that CO group, CH group, NH group, OH group, every different functional group have different frequency of vibration. That's why they will absorb at different IR absorption peak, and it gives the different peak in IR. But now in Raman, we can take the Raman spectra from any visible source, any laser visible source. If you apply any laser at certain frequency, it will collide with your molecule's material surface. Now your light will be scattered inelastically from your sample. Now if you collect the signal using the sensor, it will give a Raman spectra in terms of wave number and intensity. So generally Raman spectra give the information on molecular vibration, and in every molecule you can see that CH, NH, OH, SH, CO group are there. And since every functional group have different frequency, that means every peak will be distinct. To Raman shift are characteristics properties of your molecule. Because of this change in mass, you can see CH, NH, OH according to mu is equal to 1/2 under root k by mu. To reduce mass, if your mass is heavier, frequency is lower. According to that, different distinct peak of each functional group will be achieved in Raman spectra. So types of molecular vibration, whatever Raman and IR giving information. So actually molecular vibration can be, because for any Raman and IR peak, whatever peak is observed, you have to give a certain name to each peak. So this name actually can be given from this diagram. So like every molecular vibration can be categorized into two types: fundamental vibrations and non-fundamental vibrations. Again, fundamental vibrations which are falls into 200 to 4000 centimeter inverse. Generally, most of the Raman spectra and IR are recorded in 200 to 4000 centimeter inverse. That falls in fundamental vibration. So in fundamental vibration, generally they are categorized in stretching vibration. Means light is like stretching. Bending means if like water, there are some bending motion of angle types of motion, we call it bending. Again, stretching vibration can be two types: symmetric stretching and anti-symmetric stretching. Generally, some symmetric can be more higher Raman active, anti-symmetric vibration can be more IR active. So means any peak which are coming from this particular region, we can give it name: symmetric CN, symmetric CO, anti-symmetric CO bond. Out of plane, again bending vibration can be divided into two parts. In plane bending means your molecule vibrating in plane or outer plane. So in plane and outer plane vibration bending also give the name of your particular Raman. So meaning is that any Raman spectra recorded, you have to give certain name which can fall in this type. Again, out of plane bending, we can say this is the wagging vibrations or twisting vibration. In plane bending, we call it scissoring, like कैंची की तरह जो काम करते हैं, scissoring type vibration, or it's rocking. If molecules are vibrating like rocking dance, so we call it rocking vibration about that particular functional group. So like this is the simplest example of presentation of Raman spectra of water molecule. Suppose everybody know about the water molecule. This is the H2O, 2 hydrogen, 1 oxygen. And how many number of vibrations can be present in water? can be calculated by a simple equation of degrees of freedom, 3n minus 5 or 3n minus 6. N is the number of atom. If your molecule is linear molecule like CO2 molecule, it is linear molecule. C and O both are in linear side. So if your molecule is linear, there would be 3 into 3 minus 5 means 4 number of vibrations can be possible in CO2 molecule. And Raman and IR, you can get only 4 maximum peak in that particular fundamental vibration region. And now if your molecule is non-linear means like water. Any nonlinear molecule like water have bent structure where 2 hydrogen make 108 degree with oxygen. So now what happens? How many number of vibration can be predicted? 3 into 3 minus 6 because n is the number of atom. So 3n minus 6 means 3 number of vibrations has been possible in water molecule. And this is the characteristics property of all water molecule all over things. It means Raman shift or Raman spectra or IR spectra give the clear identification of a particular molecule. So we can say this Raman is giving the identification for particular molecule and functional group. So it suppose the water molecule that have nonlinear molecule, 3 vibrations will be observed. So first vibration you can say that this figure, my cursor is giving here, my cursor is showing here. Anybody confirm cursor is giving laser pointer?
Yes, sir, it's working.
Okay.
It's working.
Thank you, ma'am. So you can see that this is the water molecule which have bending type vibration. This bending type vibrations have some frequency. It is vibrating your molecule. Now when Raman laser light is coming, now that particular laser light will be absorbed by scattered from this particular section and a strong peak. You can see that in Raman spectra a peak is observed due to this chemical bond vibration of bending. So generally in water molecule in IR and Raman 1600 centimeter inwards, you can 1650 centimeter inwards, you are getting a peak which correspond to bending mode of water. Again, as I told you, symmetric stretching and anti-symmetric stretching. So do 2 peaks, more peaks are observed at higher frequency at 3600. Like here we can see that this is the symmetric stretching mode. This yellow one is oxygen, blue one is hydrogen. So it means that both hydrogens are coming together and going back together. This is the symmetric stretching mode, and due to this symmetric vibrations of water molecule, Raman give a peak at this peak. This vibrations corresponding to this peak. And if your molecule have anti-symmetric vibration, you can see that one peak is coming, one OH group is coming inside but outside, 1 second is outside. So anti-symmetric vibrations have peak in near about at that particular thing. So this is the assignment of particular peak. Why this peak are coming? Because of that particular vibration. So this is the basic scenario for water, DNA, protein, and whatever molecule you are going to particular material, this peak is corresponding to certain point group symmetry. So we can see that Raman spectra 3 peaks can be observed. Now if you are talking about IR spectroscopy, IR also gives the similar information. That's why Raman and IR both are complementary technique. But certain Raman have a lot of certain advantage over the IR. I am not going much detail about that. But most of the biological actually molecule are happening, chemical environment are happening in water environment, and water have a lot of interference with in IR spectra. That's why IR is not suitable for biological molecule. But Raman IR water is not a case of the interference. So that's why you can see whatever 3 peak we are observing in Raman, same 3 peak you will also observe in IR. But difference is symmetry point. You can see that हमने यहाँ पे देखा this peak is higher in Raman, but maybe that peak is lower intensity in IR. But in IR, anti-symmetric stretching can have higher intensity. But peak position like frequency should not be altered because this frequency is the characteristics properties of molecules and material, not properties of laser light. Whatever laser light, whatever light you are observing, sending to these molecules and material. So any peak, whatever you are observed, this peak is the characteristics property of your molecule. So overall, Raman and IR give the identification of that particular. Suppose we have fingerprint and you have different fingerprint. If you take the Raman spectra of our fingerprint and your Raman fingerprint, our spectral feature will be different. It means that Raman can give the clear identification of me and you different way. So this is the characteristics of Raman spectroscopy. The other mode of vibration, you can see this is the type of vibration. Symmetric vibration, you can see both are coming together. Anti-symmetric, one are coming scissoring. Scissoring means जो कैंची आप यूज करते हैं, कैंची की तरह कर रहा है इसलिए बोलते हैं scissoring vibration. This is rocking, it's rocking vibration. This is wagging. This is the twisting. So this is the out of plane bending vibration. So these types of actually vibration we can give a nomenclature for any Raman spectrum and IR spectrum peak. Not only Raman and IR also. Any peak positions you can give a certain name of that particular vibration. So we celebrate National Science Day on the discovery of Raman effect, which are observed in 1928. He got the Nobel Prize, only one Nobel Prize from India in physics to give in the C.V. Raman. How the idea come to his mind actually when he visited Europe in 1921 in a science congress. So one day he visited the Mediterranean Sea in the evening, and he see the very beautiful color of Mediterranean Sea in that particular thing. So he found that he was expecting that this beautiful color of sea is just a reflection of the sky, blue sky, but he was not convinced the explanation of Relay, because Relay already got the Nobel Prize before that Raman. But after coming to India, he started to work in a lot of sample to diffraction of the molecular diffraction of the sample. Actually, this journey of Europe to Raman actually make the history for the Indian scientist. After coming to India with his PhD student K.S. Krishnan, he started a lot of research work in this area. In 1928, he finds that every molecule has some scattering process and every time molecule is giving certain peak in that particular thing. In starting point of view, Raman thought that it is due to some error, and he submitted his paper in Nature, but that paper was rejected by the reviewer that time. But editor has published that paper in only 1 or 2 page paper that is known as secondary radiation of light. So editor generally published that paper, and now that paper actually changed the history of Indian science. Now more than 28 vibrant has been developed. So this is the discovery of Raman, 1923 to 1908. Now there's TERS. TERS का मतलब है surface enhanced Raman plus STM, scanning tunneling microscope. Give the single molecule you can directly detect by imaging process. Now more popular is surface enhanced Raman scattering. Surface enhanced Raman scattering means if any surface, if you come to the close proximity of nanomaterial, then signal of Raman signal will be significantly enhanced. So I will not come much more detail about that. I am just coming to application every area. I am not coming in that. This is a Raman effect. For beginner, you can understand. Suppose this is your molecules or material in solid, liquid, or whatever in gas stage. Now suppose any electromagnetic radiation falls on this molecule material. Suppose this is electromagnetic radiation having energy h cut omega is incident on your molecules material. If the scatter radiation have same frequency h cut omega, then we call it relay scattering. It was already known, but now after that Raman has discovered that if scattered frequency has less energy than incident photon, we call it Stokes process. Because now scattered radiation have less energy, you can say this frequency is less than h cut omega. So we call it h cut omega minus omega 1. This is known as Stokes process. क्यों Stokes नाम दिया? Because in fluorescence there is a excitation and emission wavelength there is a difference known as Stokes. Stokes was a scientist. So it was known as lower frequency, that's why we call it Stokes. And if the Raman scatter, if the light have scattered with larger intensity, larger frequency than incident photon, h cut omega plus omega 1, we call it just opposite of Stokes line, anti-Stokes. So generally finding of this Stokes line, anti-Stokes lines are known as Raman effect. And Raman is a inelastic scattering of photon by a molecular system. We can see that. Because relay scattering is different. Now this inelastic scattering is Stokes, and anti-Stokes finding is a Raman effect. And Stokes, anti-Stokes are equally spaced from the relay line. So generally whatever Raman spectra you are recording, both peak are actually we are observing Stokes and anti-Stokes, but using the notch filter in Raman instrument, we can cut the relay line and the anti-Stokes line. Means both of the Raman, normal Raman spectra are recorded in Stokes side because of low frequency, but they have larger intensity. So now only 1 photon out of 10 million photon is scattered. That's why Raman is a very weak process. Then I will explain how the nanotechnology can enhance the Raman signal using the nanomaterial. So this is a classical theory, P is equal to alpha E. You know that when any electromagnetic radiation falls in molecule, now electric polarizability induced, magnetic dipole moment will be induced in your molecule, which can be given by P is equal to alpha E. And if you expand the Taylor's function, Taylor theoretical function, then electric field also calculate. If you calculate this trigonometry, then we find that there is a coefficient of this, both equations are same. But we can see that here omega 0 plus omega B, omega 0 minus omega G. Finding of Stokes and anti-Stokes lines are easily possible in classical physics, but they have failed to explain the intensity of Stokes and anti-Stokes, because according to classical physics, Stokes and anti-Stokes lines are observed, but they fail to explain the relative intensity of both, because actually according to classical, intensity of Stokes and anti-Stokes should be similar, but which is not true. That's why classical theory failed to explain the intensity. That's why quantum physics actually explain the Raman effect. So I can explain here. In quantum physics, we can approach, we can understand your molecular system in generally ground state or excited state. So initially our molecule is in ground vibrational state. We call it V is equal to 0. Now what happens if your light, electromagnetic incident light or laser light incident on your molecular system? So now what happens? Your V is equal to 0 level can excite and go to any virtual state, dot dot dot. We can say this is dot 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 is a virtual state. Virtual is not a real state. We can assume for femtosecond or from certain time our molecule excited and go to there. And after certain time molecule, your light return back to the same state. Then we call it relay scattering. You can see the light is incident and molecule go from ground to virtual state and returning back to same state without any changing in the energy. We call it relay. And we can see that if your molecule take energy from the photon and go to the virtual state, but after radiating less energy than incident photon, we call it Stokes process. And you can say that comparative to IR signal, Raman signal, you can see that in this bottom diagram. So you can see that if your already molecule is in excited state, because few of molecule can be in excited state due to certain reason, it will go to the virtual state and come to the higher energy state, a lower energy state after radiating higher energy after taking the photon. We can solve it anti-Stokes. So we can see that anti-Stokes intensity is lower than Stokes intensity. It means that, and this is the relay peak. So generally, most of the Raman spectra are recorded in Stokes size because of their higher intensity. And quantum physics successfully explain the unequal intensity of your Stokes and anti-Stokes, because Stokes intensity is much higher than anti-Stokes. That's why any publication, any research paper, whatever Raman spectra, you can see Raman shift. Actually, it is Stokes Raman shift. People are not writing Stokes or anti-Stokes because it is common that people are regarding Raman data in Stokes side. But for particular application like coherent anti-Stokes, non-linear Raman, many techniques which are also important for anti-Stokes side, like coherent anti-Stokes Raman, for ultra-fast vibrational dynamics, 10 to the power minus 15 second information you can withdraw from molecule, then anti-Stokes Raman line can be also helpful. So this diagram actually clearly indicates that Stokes have larger intensity because of this quantum effect, and this is anti-Stokes. So most of the Raman spectra recorded in Stokes side. So this is the first Raman diagram where CV Raman actually started to get the Raman signal. That time laser was not invented. Laser was invented in 1974. So he used just simple mercury light as a source of the light, from where light excites the molecule and they have scattered the sample. The first Raman spectra they have using the photographic plate, not in that particular spectra. So this is a filter orbital. First spectra, actually this spectrum instrument is still put in ISS Kolkata. So this is the topic of CV Raman, which was published in Nature in 1928. A new type of secondary radiation. I am not coming too much. This is the simple demonstration of Raman's instrument, where laser light is there, incident, laser light incident on fringe selector, any light which are incident on from laser to any molecular system, and there are certain rotating sample from here from photo lens to slit opening, go to the monochromator, and to monochromator to go charge couple detector, and then you can get the Raman. This is the Renisha Raman spectra, where you can put the sample here and signal are coming there, and there are 90-degree and 180 scattering geometry will be there. So according to your requirement, you can detect the Raman signal of your any molecule and material. You can put here and take that. So after taking the Raman spectra, you are getting the information on 3 parameters. This is the simplest thing for beginner. We are getting x-axis, y-axis data. X-axis shows the peak position, y-axis shows the intensity. And here we can see that this line width showing the full width half maxima, and this line width shows the dynamic nature of the molecule. And this finding of peak position shows the static nature of the molecule, means how the molecule interact, what is the force constant, what is the charge distribution, and what is the functional group, like CO group, CH group, NH group, OH group. Actually, these are defined by this frequency position. And intensity variation shows the any material like doping, or you are mixing nanomaterial in any particular material. So what is the load? What is the percentage of loading or doping of concentration? Actually, intensity defined. Increasing or decreasing intensity define the loading or amount of material present in your system. So these 3 parameters, you can analyze all the information about the Raman. So as I told, this is line shape analysis. Wave number shift shows the nature of interaction. Either 2 molecules are attractive or repulsive, actually defined by your frequency. Frequency shift, suppose any in pure molecule, what is the frequency and what is the happening after interacting with molecule? It depends on your nature of interaction. Accordingly, peak position can be shifted. As I told you, line width calculation already also give a lot of dynamic property. You can find out the dynamic property, this what is happening in nanosecond order or picosecond order in your molecular system after analyzing the dynamic property by this line width. Intensity actually give molecular association all over this, make a Raman signal spectra structure correlation. Means using the Raman and IR spectra, you can correlate the structure. That's why we call it spectra structure correlation using the Raman. So now this was the basic thing. I will complete my basic fundamental part. Now I am coming to application part. Sir, please remind me 10 minutes before, because I have a lot of slide. Accordingly, I will finish.
Yes, sir. Yes, sir.
So now Raman spectroscopy, simplest example I am going to give you molecular interaction. Because a lot of people actually mix 2 molecule or molecule in DNA, protein. So not I am going to, coronavirus is also molecule. Because COVID, coronavirus or dengue virus, they are also some types of molecule. But huge molecule, you can also giving the observation of many peptide peak and proteins peak. So I am giving very simplest example of molecular interaction between 2 molecules. I am suppose giving this example of spectra structure correlation. Suppose we have simplest example, acetonitrile molecule. Acetonitrile molecule have spectra molecular structure CS3 C triple bond N. This is acetonitrile. We have dominated by C triple bond N polar group. Now, suppose we are taking the Raman spectra of acetonitrile by Raman spectrum, then this first spectra, you can see that this is a pure acetonitrile Raman spectrum. If you analyze this Raman spectra using origin, then we can find 2 asymmetries observed in lower wave number side and 1 is here. So when we analyze this Raman spectra, we found that this Raman spectra give information that pure acetonitrile molecule are finding in dimer form. Dimer form can be easily observed by this Raman signal. आप देख सकते हैं this smaller peak showing the dimer nature. Make dimer का मतलब acetonitrile molecule make hydrogen bond with same molecule. You can see in left side this acetonitrile molecule, this CN, and other CH group it interacted with same molecule acetone by the hydrogen bond. So means this hydrogen bond we are getting this smaller peak in acetonitrile. Now suppose I am going to mix some alcoholic solvent like methanol in that particular acetonitrile in some molar fraction. Suppose 50% molar fraction acetonitrile is dissolved by alcoholic solvent methanol. हमने क्या किया यहाँ CH3OH mix किया 50%. So what happens? You can say that Raman spectral features has been changed. Whatever this peak intensity of dimer is decreasing, and what happens? A new peak is observed on higher wave number side. This new peak is observed on higher wave number side. because of interaction of acetonitrile with methanol molecule as a hydrogen bond. And Raman spectroscopy give clear identification about that hydrogen bond formation between two molecules by giving another extra peak. हम देखिए नीट में नहीं था ये peak, यहाँ पे आ गया. And whatever, if you increase the concentration of your solvent, methanol, then what happens? You can see the intensity of this hydrogen bonded methanol has been increasing, and the dimer formation intensity is decreasing. It means that the dimer network or trimer network is decreasing, and now acetonitrile are ready to make hydrogen bond with methanol. And this types of hydrogen bond between acetonitrile and methanol take place, and that's why a new peak due to hydrogen bonded complex has been formed. It means Raman spectra clearly identify the formation of interaction and hydrogen bond between two molecules. क्योंकि आप यहाँ नीट में देखिए, there is spectral feature of neat and spectral feature of interacted molecule with any. The similar way, this is example. Now you can DNA, protein, or nanomaterial, yeah, doping, whatever you are telling about that in system. Raman spectroscopy clearly identified either by line width change, either by frequency shift, either by intensity variation, and we can draw on every information about your molecular system. If there are some impurity or if you are mixing particular thing, then you can find out. Because we are focused on here only C triple bond N group, not whole Raman spectra. That's why you can see. So everywhere you can find out spectra. Similar way, existence of DMSO. DMSO is a very simple molecule, dimethyl sulfoxide. This one structure is DMSO. Actually, it was my first paper as a corresponding author when I was in PhD. That's why I saw this paper result. Very interesting result I found that, because I found a DMSO as a magic bullet for cancer. I read an article in Times of India कि why magic bullet for cancer. In biological reaction enhance the quality and shows a lot of medicinal property, and DMSO is a very normal solvent available in every lab. So I thought that what happens, why DMSO is so popular or so important for magic bullet for cancer. So immediately I take the Raman spectra, finding that in pure Raman spectra of DMSO, you can say that again two peaks are observed, and I am using the DFT, Raman and experimental DFT, experimental Raman and DFT theory. I have compared and found that DMSO not only exists in dimer, even trimer form, and I have proved in Raman spectrum figure here within dilution with water. This is the pure, and in bottom you can see that DMSO, in bottom this is the DMSO pure, and upper side you can say that strong dilution with water. The spectral feature you can see very, very different. Peak position you can see here 1045 centimeter inverse. You can say this cursor 104, but now this peak is shifted to here 100. Means you can say that 40 centimeter inverse huge shift of your SO group from mixing with water. So it means that Raman shift clearly identifies the interaction between two molecules, how the spectral features are changing. So a simplest example how you can calculate the Raman spectroscopy with fraud material. So now suppose any material like simple pearl material I am giving. So this is the top spectra, Raman spectra shows the Raman spectra pure pearl, and bottom spectra shows the Raman spectra for forgery pearl. Means if there are a lot of impurity mixed in your pearl, then Raman spectroscopy clearly identify the identification of your pure pearl or forgery pearl.
Sir, you have to conclude in 10 minutes now.
Okay. So this is the fingerprint. As I told you, every person have different fingerprint. You can identify it. So variants of Raman spectroscopy, I told you a lot of 25 variations has been developed, but I am coming to Raman application in carbon-based material. You know that carbon is one of the most abundant element on the universe, and now addition of new dimension like carbon nanoscience, like fullerene, graphene, and carbon nanotube. Actually, it added the new dimension in the carbon nanoside. So now carbon-based nanoside has a lot of application in energy, water purification, pure water treatment, electronic circuit, energy storage material, battery, supercapacitor, like a lot of application of graphene in every area, lithium-ion battery to every area. So now I am going to explain the application of Raman spectroscopy in carbon-based nanomaterial. Because without Raman, Carbon-based nanometal cannot be characterized. Same time you can see the morphology, but how many number of layers, how carbon nanotube or fluorine has been characteristic property, it can be only characterized by Raman. So this is known that what is the 3D, that is diamond, that is a 3D, means a bulk form. If you are, this is a graphite bulk form of carbon. If you are taking the single layer of graphite, if you cut the single layer of graphite from bulk to nano, we call it graphene. Graphene is a 2D nanomaterial, single sheet of 2D, and this is the just you fold the graphene in nano carbon nanotube form, with cylindrical form, we call it carbon nanotube, which is one-dimensional material, and this is a fluorine that has zero-dimensional material. If carbon 60 element are making in a football-like structure, we call it carbon 60. All carbon are made by CC bond, and all CC bond have chemical bond vibration, and Raman spectra can give the clear identification spectra about that. So now I am going to show you how the Raman spectra are able to characterize the different layer or carbon nanotube or fluorine. So this is the Raman spectra. You can say that this is the pure graphite bulk form, and this is the one layer. How the spectral features are changed, 1 layer to 2 layer, 5 layer to 10 layer, spectral features has been changed. According to this, you can identify the number of layers, which are not easy characterized in HR time or structure time. But Raman spectroscopy clearly identified number of layer in your system. This is the graphene and this is the graphite. So in generally graphene, a G band and 2D band is observed. G band means graphene band or in plane bending vibration actually are observed at 1500 centimeter inward, and graphene band or 2D band will be observed. And suppose if you graphene band, if you are any deviation from sp2 hybridization, हमने क्या किया, graphene को थोड़ा सा मोड़ा, yeah, we are giving any defect in that particular sample in graphene, immediately Raman give a spectral and the D band peak. Means a new band will be developed at 1300 centimeter inward corresponding to D band. D band disorder being a defect peak. तो जैसे ही आप ग्रेफीन में कोई भी फंक्शनलाइज करेंगे C2, O2, N2 or any folding of graphene, you can immediately find a D band in the Raman spectra. You can identify. So this is also find out graphene oxide and monolayer graphene. Monolayer graphene, you can see that only G band will obtain. Graphene band in plane bending vibration, G band here. But when graphene oxide is there, I am again saying in graphene you are oxidized, means like oxide, graphene oxide, immediately you are getting another peak, D band. Means defect or disorder band due to this oxide peak, a G band according to D band will be observed. So means Raman spectra clearly identified about graphene, graphene oxide, graphite, graphene oxide, reduced graphene oxide using the Raman spectra. This is the again Raman spectra of carbon nanotube, because now carbon nanotube is made cylindrical form. So now radial breathing board, RBM breathing bed can be coming, and you can calculate their metallic form, semi-conducting form, multi-layer form, single form, every type of form using the Raman spectroscopy. This is a graphene quantum dot. You can see the size of this graphene quantum dot is 1, 2, 3. You can see that if you are increasing the size of graphene quantum dot, then it will be implemented in Raman spectroscopy. Raman clearly बता देगा कि ये 1 का है, 2 का 3 है, and how many number of functionalization group if you are increasing in different group you are adding, then you can find out after analyzing, you can find out different functional group available in your graphene quantum or quantum dot. So now I am coming age functionalization quantum dot. As I told you, many group if you are functionalized simultaneously, then a lot of D band and G band can be obtained in Raman here, and you can analyze and correlate your structure. So this is the 2D material. As I told you, now 2D material giving the number of layers, how the number of layers can be find out in layer. So this was the conclusion for Raman. So I think surface enhanced Raman, I have no much time, so I am not coming in surface enhanced Raman, but shows the just application of search. How the surface enhanced Raman spectroscopy can detect the explosive element. Generally, terrorists use the RDF or toluene, TNT, RDF actually for the explosion in the human population, and it is very dangerous for now. Small quantity contaminant in water or underground water can be very harmful for human disease, a human problem for a lot of cancerous issues. And now suppose after explosion, generally forensic people collected the data. If one small dust you can collect it, and you cannot take the Raman spectra of one dust. But what happens in surface enhanced Raman scattering? Just you have to make a nano substrate, nanomaterial, simplest metal nanoparticle or bimetallic nanoparticle. Just make, and if you put that dust on that metal nanoparticle without changing any property of that particular molecule, the signal, Raman signal, can be significantly enhanced. So we call it surface enhanced Raman. So RDX and whatever molecule, because RDX is also molecule and molecule have chemical bond vibration. तो जैसे ही हम उसको रखेंगे वहां नैनो पे, so now you can get the Raman spectra and we can identify that this is RDF, TNT or another explosive element. Either although in groundwater it is available in water or not, you can identify it by the Raman spectroscopy with nanotechnology. So a lot of process to identify it. I'm not coming to that particular thing, but this is the protocol. And same way uranium. You know that uranium is a nuclear source. This source, a lot of nuclear weapons actually use uranium oxide. So it can be contaminated to our drinking water. So from drinking water, how you can make contamination can be detected by with single molecule detected by Raman. Again, using nanotechnology and Raman signal, we can find out with this peak, certain peak, marker peak, we can identify the contamination of that particular thing. So now I am. This is a polymer, like self-healing polymer, can be calculated by Raman. Application Raman in biomedicine, as I told you, because biomedicine, a lot of molecule, DNA, protein, or any influenza virus, hepatitis, means whatever virus is there. Virus is also sometimes a molecule, and molecule have chemical bond vibration, and it can be given by them. Like simplest example, you can also detect healthy cancer and healthy skin and cancerous cell. Cancer cell and healthy cell you can identify by Raman, and you can find out there will be certain difference into that particular. And every peak is corresponding to certain protein, glycoprotein and protein lipids, whatever DNA, RNA, you can identify by certain. So biological sample can be also. This is the example of dengue infected blood serum and non-dengue blood serum. You can see red one is dengue infected blood serum and blue one is non-dengue healthy blood serum. So means you can compare. So by comparing the Raman, you can also find out the difference between dengue infected blood or non-dengue. Similar way virus. So I am not coming non-linear Raman. This was the actually non-linear Raman spectroscopy when I was working in Germany. I was working in non-collinear Raman. So I am not. Last things I can explain the coronavirus. People are also trying to detect the coronavirus using Raman spectroscopy. This is the coronavirus structure. It is nothing. There is a protein, S protein, E protein, lipid bilayer, M protein, which are also molecules. It means Raman spectroscopy can clear giving the. So now people are making the device, portable device. Portable device means pen types of device to identify these types of structure. So people have already devised SARS-CoV virus for known faster cards things. It is a direct identification of single virus using coherent anti-Stokes scattering. So they have actually put it 3 types of virus together, and they have collected the Raman spectra, that is green and blue color, and they have identified what is the spectra corresponding to which virus, influenza virus or something like. Again, people are making a virion devices where nanorod, silver nanorod they have taken on the surface virus, nanorod is there, this is the nanorod surface, and they have detected that particular viruses on that particular scene. So I think I will conclude. Concluding is by that Professor Kiefer, which is a known Raman spectroscopist, said and wrote, I am asking myself, what cannot be done with Raman spectroscopy? A wonderful analytical tool for science and technology, which was discovered by Sir C.V. Raman and Krishnan already 8 decades ago at the Indian Association, ISF Kolkata. I am looking forward to many more years of significant advancements in this year. So advancement of Raman spectroscopy may be a non-destructive, non-invasive real-time monitoring tool for COVID-19. So meaning is that Raman have already a lot of application in all research area. More than 28 technology has been developed based on the Raman spectroscopy for various types of material characterization. So I will recommend a book, Raman spectroscopy book. Actually, it is written by our collaborator Ashish Mishra, ITBHU, and Anup Metterji, my collaborator from Germany. In this Raman spectroscopy book, last year we have published a lot of things has been given. A lot of things has been given, basically starting from basics of Raman, normal Raman, resonance Raman, surface enhanced, coherent resistive, means 12, 13 chapter based on Raman techniques, variants of Raman techniques is given. So you can read it, and other books are also we have published. So I thank all my collaborator and organizer and my PhD student and research group. Thank you very much.
Thank you, sir, for your expert lecture on Raman spectroscopy and its applications. The session is now open for question and answer.
Any basic question a student can ask or write in the message box.
Sir, there is a question from Rajesh Kumar. How can we calculate sp2, sp3 rotation of carbon bonding via Raman spectra?
Yeah, actually, you know, this graphene, suppose graphene is a single layer of graphite. Graphite क्या होता है? Multi-layer of graphene is known as graphite bulk form. Now, when you are synthesize graphene, it is a single layer of graphite. So single layer of that is make of CC bond. CC bond, it is already sp2, sp3 hybridization. sp2 hybridization means carbon-carbon is very known that hybridization is about it. But now, main important is how the hybridization is changed. इट कैन बी कवर्ड बाय द रमन. कैसे होता है? जैसे आपने सिंगल लेयर किया, आपने इसमें क्या किया, एक नाइट्रोजन रख दिया. नाउ इलेक्ट्रॉनिक स्ट्रक्चर इज चेंज. नाउ रमन स्पेक्ट्रा immediately of that ki hybridization is changed, electronic binding is changed. That's why a peak will immediately started to come in Raman spectra known as D band. क्योंकि जो ग्रेफीन है उसमें खाली एक बैंड आएगा, G band. G मतलब in plane bending graphene band. Some people call it graphene band, some people call it in plane bending vibration. ऐसे करता है. लेकिन वैसे ही आपने उसमें हाइब्रिडाइजेशन चेंज किया, डोपिंग किया, a D band disorder peak will be obtained. If D band actually give you identification of sp2 and sp3 hybridization.
There is another question from Rajesh Kumar. If laser source UV and visible 325, 785 changes, then D and G 2D peak position or intensity will change?
Yeah, intensity can be changed. That's why if you people understand surface enhanced Raman scattering, actually I did not explain about that. There are two processes, electromagnetic enhancement and charge transfer mechanism. So electromagnetic enhancement actually 80%, 90% dominate over the charge transfer. But in charge transfer mechanism can be explained by the potential or laser dependent property. If laser intensity, if you are changing, or laser wavelength is changing, actually according to normal Raman spectra for any molecule material, your peak position intensity should not be changed. For normal Raman spectra, as I told you, it should not be changed. Because Raman shift is the characteristic property of the molecule. अगर वाटर की जो प्रॉपर्टी है, मेरे फिंगरप्रिंट की जो प्रॉपर्टी है, कोई भी लेजर डाले, it should not be changed. Peak position should be same, but only in IR and Raman peak position intensity can be changed. But in carbon-based nanomaterial, many report actually reported that changing the wavelength dependent property, metallic and semiconducting property can be changed. Actually, there are some certain charge transfer mechanism, you can say potential dependent surface study. So in change, some cases we can for purpose study of multi-layer, single layer and particular material characterization.
Hello, sir.
Hello, Nirvaji.
Yes, sir. Good evening, sir.
Good evening.
Sir, one question also from chat box. What is the physical origin of D and G and 2D band in a carbon material, and how do their activation mechanism differ?
B and G?
D, G and 2D bands in carbon material, and how do their activation mechanism differ?
Oh, now they are confusing with D band and 2D band. Actually,
Yes, sir.
as I told that some people call it 2D band or some people call it G dash band. Actually,
Yes.
what happens, that is a overtone. Like as I told you, in fundamental vibration, there are 200 to 4000 centimeter inward, but there are certain doubly resonant band are occurs in carbon nanotube. So generally in Raman, actually every peak like 1000 you are getting some overtone or combination band of 1000 means more than 2000 or below to 2000 you are getting although overtone of that particular band. But in carbon nanotube, what happens? And G band, graphene band, that is in plane bending vibration, so just double peak of 2600, something like that. It double resonance, you can also peak at something. Like same with D band and 2D band. So D band means that is disorder, it means defect. You are giving a deliberately defect your material. Yeah, just functionalize that material. You are getting D band. And again, W resonance 2D band can be obtained. So generally, the ratio of G and 2D band, actually many expert actually calculating in paper, D band and 2D band, or G band and 2D peak ratio, intensity ratio, they can actually identify the number of layers. How many number of layers are present in our sample, because after growing the 2D metal you cannot see by naked eye, and our HR time also not identify that particular growth. But Raman clearly identified by ratio of that intensity D and 2D, G and 2D band. Intensity variation can identify how many number of layers are present in your system.
Yes, sir. And one more question, sir. Why does the G band position shift with increasing number of graphene layers?
Yeah, number of graphene layer they are shifting. Simple ये things है. One graphene layer is there.
Yes, sir.
Graphene and many graphenes are connected by stacking. We call it graphite. हम graphite ही बोलते हैं bulk form of carbon. जो पेंसिल होता है suppose this is a graphite. और उसमें से हम एक लेयर निकालते हैं तो ग्रेफीन, तो कई लेयर हो गए, मतलब मल्टी लेयर, मतलब वन ग्रेफीन लेयर इंटरेक्टेड थ्रू द पाई स्टैकिंग. पाई बॉन्ड मतलब द बेंजीन रिंग का जो बीच का बॉन्डिंग होता है, नॉट केमिकल बॉन्डिंग, दैट इज अ पाई स्टैकिंग. वी कॉल इट पाई स्टैकिंग इंटरेक्शन. तो अब व्हाट हैपेंस इन रमन, एज आई टोल्ड यू, during the molecular interaction, if your molecule interaction is attractive or repulsive, according to that wave numbers can be shifted. अगर wave number lower side जा रहा red shift or higher side जा रहा blue shift, it depends on nature of it. So now number of layer increases means number of hydrogen bond is increases.
Basically, sir, electron phonon coupling के terms में भी explain कर सकते हैं.
Any more question?
No, sir, no.
No, sir. All questions have been answered by you very well. Well handled by you. And now I thank you once again for a wonderful expert lecture and your valuable time you have given to us. Thank you, sir. Thank you once again.
Thank you, Ashish ji. Thank you, Nirbhay.
So we are now commencing the fourth session of the initial workshop on advanced characterization tool and technique for material science engineering. To formally begin the session, before inviting our distinguished speaker, Dr. Rishi Sharma, sir, may I have privilege to introduce him to the gathering. Dr. Rishi Sharma, currently working as a principal scientist in semiconductor sensors and microsystem group at CSIR Siriplani. He is currently working on design and development of MEMS-based microsensors for chemicals and biosensors. Apart from this, he is also working as an assistant professor in ACSIR in Siriplani. He is also an adjunct faculty at IIEST Sripur. Before joining CSIR Siriplani, worked as assistant professor in Amity University, Noida from October 2009 to April 2010. He received an MSc Electronics and PhD Electronics from Jivaji University, Gwalior, India. He has obtained a research fellowship from University Grant Commission, New Delhi, and from DRDO, India. During the PhD, he worked on the development of organic material-based detection system for toxic agents. He has published 70 research papers in international and national journals. Dr. Sharma has also co-authored one book chapter. He is a lifetime member of the Instrument Society of India and member of IEEE USA. Please, sir, grace us with your expert lecture.
Hello. Am I audible?
Yes, sir, you are audible, sir, and visible also. Welcome,
Thank
sir.
you. Thanks to the organizer first of all, for giving me opportunity to present one of our research work. Let me share my PPT. Is it visible?
Yes, sir, visible.
Visible, sir.
It is in PPT mode?
It's PPT mode, sir. Presentation, not in presentation mode.
I hope now it is in presentation mode. Hello?
Yes, sir.
It is in presentation mode now?
Not in presentation mode for now. Maybe there is an internet issue, so that it's got stuck.
Let me. Just a minute.
ऋषि सर स्क्रीन शेयर करिए आप कंप्लीट स्क्रीन ऑफ योर लैपटॉप.
Now it is visible?
नहीं, not slide. Yes, now okay, perfect.
It's
Okay.
visible, sir. Presentation.
Okay. Thank you. All right. So I am presenting one of our research work related to the characterization of thin films using FSM. FSM stands for film stress measurement. Normally, when we are fabricating microsensors, basically they are to do with the MEM sensor, that is micro electromechanical systems. So we are fabricating sensors like cantilever or accelerometer or ultrasonic transducers. So while fabricating the stress analysis of those films is very, very important and essential, because as a designer and as a person who are fabricating devices, it is important to understand the overall stress. When, as you know that say we have silicon wafers, on that we deposited many films, and typically they are the oxide is grown like silicon dioxide, followed by like PECVD oxide or nitride, LPCVD nitride, or we have a sputter deposition of various films, piezoelectric films, or we have oxide films, or that matter like silicon dioxide. We have tin oxide, aluminum nitride. So these type of films, their temperature of coefficient of expansion are different. So when we deposit the multiple layered thin films on any substrate, the overall stress analysis of that film is very, very important, as ultimately when we design and fabricate the MEM sensor, we tend to have a hanging diaphragm. So the stress optimization, overall stress optimization is very, very important, because I will discuss it in our results also. So this is the outline of the presentation. It is about the thin films, whatever thin films which we are using. Then residual stress, and what are the reasons for the generation of those residual stresses, and what are the evaluation techniques which are used for the evaluation of those stresses. And then we in our lab we are using the FSM technique, that is the film stress measurement technique. And there is another equipment called nano indentation, which is one of the also well-known tool for the analysis of elastic properties of materials using nano indentation technique. So we have characterized our samples at IIT Kharagpur. So as I already discussed that, for that matter, like if we are fabricating pressure sensor or ultrasonic transducer, just a moment. As you can see on right side, there is schematic diagram of pressure sensor and ultrasonic transducer. You can see that there is a diaphragm and there is a cavity inside the diaphragm. So basically these type of structures were realized either by SOI, silicon on insulator wafers, SOI wafers, or by the bonding of the two wafers. We process two different wafers, and then finally these wafers were bonded together for the creation of cavity. Now, resonant frequency is one of the important parameter in MEMS devices, and resonant frequency may get shifted due to the residual stresses in the film. So when we are designing for any specific application and we are targeting any particular resonant frequency or the targeted frequency, and we design that, we simulate all those parameters, and then accordingly we decide the fabrication process flow. So if the residual stress will be there, then the resonant frequency will get shifted. So whatever we target, that cannot be achieved until unless we will understand the overall generation of residual stress in the stacked film. So for that matter, as I have shown, that the resonant frequency is dependent upon the membrane thickness. It depends upon the cell radius and the residual stress. So residual stress is not directly exist, but it is like a uninvited guest in the fabrication. So to understand that, we have done this study. So as you can see that when a thin film is deposited on a substrate, mechanical stress will introduce. To relieve that stress, the substrate will get bow. It will, either bulk up or bulk down. As you can see in the diagram on the right side, A and B, these are depicting the tensile and compressive stress. So when the tensile stress is there, there will be buckle up of the wafer, and compressive we tend to have a opposite nature. So as you can see that we have taken the substrate on which any film is being deposited and the stress is being taken up. So the effect of residual stress developed by the thin films on substrate, they actually tend to change the curvature. So when we are using indirect techniques like FSM, because FSM is measuring the radius of curvature of the wafer. So whenever any wafer is being procured, very first thing is a very important parameter is like doping concentration, the type of wafer, or the either we are using 100 or 111 wafer, what type of wafer which we are using, and what type of doping concentration is there. And the very important parameter is bow. What will be the bow of the initial wafer? So first and very most important thing is that we should have a wafer which is having the lowest possible bow. So FSM will going to measure the radius of curvature of the wafer, and based on that it will identify either it is tensile stress or compressive stress once the next film is deposited on that wafer. So as I said that how the residual stresses they generated inside the thin film or the stacked of film, this is mainly due to the epitaxial stresses, or we can say that the lattice mismatch between substrate and thin film. If there are lattice mismatches, then they tend to create stresses. Then we have thermal stresses. Thermal stresses is to do with the thermal expansion coefficient of substrate. When the two films they have different TCE, and we are going for high temperature deposition, then the two films or three films, when the TCE is different, they tend to have stresses. So another aspect for the creation of that stresses is the thermal stresses due to the different TCE. And the intrinsic stresses in thin films, it happens due to the voids during the growth of the silicon wafers or the growth of the substrate. For that matter, like the type of wafers which we are using, in case of like silicon wafers, it is grown by the CZ technique or the float zone technique. So FZ technique silicon wafers, they are very costly wafers, but they are the least defects in those films. So the selection of the substrate is equally very, very important for the initial mitigation of the residual stress or the reasons for the generation of the stresses. So the base substrate should be free from that. So the three possibilities for the generation of residual stresses, that is the epitaxial stresses, thermal stresses, or the intrinsic stresses. And then how and when stresses are introduced, how this will going to create problems. It leads to the cracking of the deposited film, or delamination or buckling, or the metallization hillocks, which will lead to the short circuit or the failure of the device because for contact, for the electrical contacts, we also deposit like gold or aluminum as one of the films. So if the metallization hillocks will happen, then there will be a possibility of shortening of those tracks and the voids. So these are the causes of those stresses. As you can see in the diagram, there is a shifting in the resonant frequency. As you can see in the B figure, the different stresses, when the residual stress is built up, the resonant frequency is shifted. So as I said that during designing, when we are targeting a certain area, for that matter, in this particular case, we were targeting, say, using ultrasonic transducer for studying the properties of liquids. If we are putting our device in liquid environment, the inherent stresses and as well as the stresses build up due to the fluid will affect the device performance. So based on those applications or the kind of application, we have to target its resonance frequency, right? And for resonant frequency to achieve that under that environment, we have to understand the residual stresses because it will lead to the shifting of the resonant frequency based on those stresses. So these are the evaluation techniques of residual stresses. How we are going to evaluate it, as you can see that in the diagram, when any film is deposited and in the center of this you can see the interatomic distance of the deposited film is uniform. When it is uniform, we can say that it is having no strain or no stress. If there is a uniform strain, then the interatomic distance is uniformly elongated or compressed. But uniformity is there. And when it is non-uniform stress, the interatomic distance will be different in top layer to bottom layer and kind of thing. It is only diagrammatic representation. So evaluation of residual stresses can be done by wafer curvature technique, as I said that this is the non-destructive techniques also, because we are measuring it by the wafer curvature. What I mean by wafer curvature is this: as you can see that the initial ROC, that is the radius of curvature of a substrate, and when the thin film is deposited, and this is, we can say that is the final ROC, the radius of curvature. So when these substrates, they are put in the system, that will characterize its ROC, pre-deposited and post-deposited. Okay. So wafer curvature techniques, they can be done by direct contact based stylus profilometry, or by the non-destructive or indirect technique with the use of the laser scanning technique. Another analytical technique which is well known, which is being used, is the XRD and Raman spectroscopy also, or cantilever based deflection methods can also be utilized, can also be used. Then we have like piezoelectric resonant method. So these are the various techniques through which we can able to identify the stresses. As you can see in the center of the diagram, there is a sharp peak is there. This is the case with the XRD, and the sharp peak is there, and the sharp peak is when there is a uniform stress. It may be tensile or compressive. These sharp peak will either shift left side or right side to theta angle. And in case of non-uniform stresses, the full width half maximum of the peak will get broadened up. So these are the indicators. So through XRD also the stress analysis can be done, but also through FSM techniques. Another method is the nano indentation techniques. So nano indentation technique will measure the elastic modulus and hardness of the deposited or grown film on any substrate. That actually in this particular case, we used to put our process wafer inside the system, as you can see on the right side, and there is one tip is there, which there are three types of tips they are being used, and that tip is touched on that wafer. presses it and generate with certain force. And then there is a loading and unloading curve. And with the help of that loading and unloading curve, the stress is being evaluated. So we can say that the displacement control method is used to obtain the Young modulus, or as I said, that the elastic parameters of the substrate. So these are the tool specifications and typical temperature ranges, and this is the tool which we have used at IIT Kharagpur. So in this particular case, this is the standard formulas, which is the ER is equals to square root of pi by 2 multiplied with the S divided by that. So AC is the tip area. So in this particular case, we have used the Berkovich tip, and there are the three type of tips they are being used, and they are based on the type of film we are going to characterize, right? If it is there is a conical tip also. So based on the soft material or hard material, whatever material which we are going to characterize, based on that, the tip selection is being done. So in this particular formula, the AC is the indenter tip area, which is the Berkovich tip which we have used. So ER is the reduced Young modulus, and this you can see on the right side of the depiction. There's a thin film, and there is a tip which is pressing that film. So you can see that the certain force is being applied, and the loading and unloading is being done. Okay. So once it is pressed, and then it is moved away from that. So the tip will create a deformation on the top film, and then once again when that tip is pulled out, this will try to regain its original shape. So the loading unloading curve is there, and you can see on that the slope is being identified, and this slope value is being substituted in the ER formula, and the Berkovich tip area is the standard value, and based on that we evaluate the ER. This ER can be substituted in the next formula, and through this is the when you notice this formula, the very first part is related with the Young modulus of the indenter tip, and the right side is to do with the sample. So with the help of this formula, we can able to evaluate the Young modulus of the composite film. If we have like one layer is being deposited, or the two layer is being deposited, so that will give the overall composite Young modulus of that film. So with that, what we have done is we have taken many wafers, and we started with the evaluation on silicon wafer. First we deposit the silicon dioxide, then PECVD oxide, nitride, and those same wafers were separately batch is prepared, and independent wafers parameters were being taken, and we have find out the Young modulus of that film. So this is to increase the accuracy, and typically when we are dealing with the nano indentation tool, typically it takes say 8 to 10 scans. So at the equidistance level of say 50 micron, and this tip collected data, and these are the parameters of the silicon wafers which we have taken, like 3-inch silicon wafer, and I said that FZ wafers are very costly, so we have taken the CZ wafer at this point of time. This is equally good wafers, and this is double side polished wafers, 100 orientation. So we have evaluated the young modulus as 186 in this particular case. This is like the averaging is being done when we have taken the multiple wafers, and also in the same wafer we take the data at multiple points, and that is being averaged out. So this is another equipment, so that is the FSM. So we are comparing the FSM data and the nano indentation for getting the accuracy, higher accurate stress evaluation. So in this particular case, FSM is the standard tool which we can accommodate 2 to 8 inches of wafers into it. So we have used FSM 128, which is based on the two lasers of 650 nanometer and 780 nanometer wave lasers were being used. And as you can see on the right side, there is a stage. Wafer is placed on that stage, and at 3 raster scan is being done, and the data is being collected, and then it leads to generation of ROC, radius of curvature of that wafer. So if this is the wafer and the laser is fall on that, so it will generate the radius of curvature. This is the radius of curvature of that. So I just missed that diagram. If I should have put it. So that will generate the radius of curvature of that wafer. So this is the FSM. We use standard formula for the calculations. This is the Stoney's formula. So in this particular case, you can see that the substrate Young modulus is being substituted in this particular formula for the calculation, and the RF and R0 are the radius of curvature of initial and final substrate. For that matter, we have like silicon wafer, and if we deposit the silicon dioxide, so first we will take the radius of curvature of the pre-deposited, that is a plain wafer. Then we deposit the silicon dioxide on that, or grow silicon dioxide on that, and then we take another scan that will generate the RO. So with the help of that, we can able to calculate the parameters. So this is we have taken, like as I said, that we have taken the 8 scans of the same wafer to generate the accurate result. So this is the particular case of silicon dioxide. So the left hand side is the film for the reference scan. As you can see in the previous formula, when we are calculating the overall stress of the film, we have to take the pre-scan of that film. So that means in this particular case, we are trying to find out what are the type of stresses it tends to create. So we deposit the silicon dioxide. First, we take the bare silicon ROC, and then after deposition of silicon dioxide of 1 micron growth, we have done the scan, and then the averaging is being done. So this is the final result which we have evaluated for the various films. Like as I said, that it is the thermally grown silicon dioxide, then LPCVD polysilicon, PCVD silicon dioxide, and PCVD silicon nitride. We have chosen these stacked film because in our process, these all stacked film is being grown or deposited. Therefore, we have taken these films. It is intentionally taken these films based on our device parameters. So we could able to find out the residual stresses, and based on that, the results, we have redesigned our specifications and process parameters and mask layout. So this study gives conclusion. The laser-based scanning technique provides a non-contact, non-destructive inline measurement of thin films. Why this is important? We have very first we have designed it, then we have checked it by doing experiments, and then we have checked whether the specific resonant frequency is achievable or not. If it is not achievable, we have to calibrate the design, and based on that, the correction is being done. The thin film, thermally grown silicon dioxide, LPCVD, polysilicon, PECVD oxide, ECVD nitride under test shows compressive nature of stress, and these values are there. So maximum thickness variation of the substrate was of the order of 1%, which can lead to a maximum variation of 2% stress values. Hence, it is recommended to use the total thickness, low TTV. As I said, that the wafer selection is very, very important. So we have to be very cautious for the selection of our wafers having the low TTV. So these are the acknowledgements to our Honorable Director and the DST, the funding agency for this project, and the SSA, Division of CSA. So these are the references. Thank you.
Thank you, sir. Thank you, sir, for the wonderful presentation. The topic of layer technology. Would like to thank you, sir. And now the session is open for your questions and discussions. If there is any questions, attendees can ask in the chat box. You can type in the chat box.
Dr. Nirvay, I need to ask any question that is in the chat box.
No, sir, I think there are no questions.
Okay.
Panel member can also ask question to sir. This is good chance for us.
Sir, I have a question to you. Hello.
Please.
Sir, what kind of stresses we are going to calculate? We should calculate for the thermal barrier coating, if you know about this topic.
You're talking about the thermal sensors or what?
Thermal coating to prevent the material, the monolithic material, to prevent monolithic material from thermal exposure. We have to.
Then you have to understand the overall, stresses, because some of the coating is being done, and the micro cracks they may generate. So you have to understand the composite property of that material. What will be its behavior at higher temperature? It is compressive or tensile. It will, based on that, the base material which you are using, on which your coating is being done. So you have to understand and check the TC of the two films. If they are opposite in nature, they will tend to create cracks. If one is compressive, another is tensile, then you have to check that.
So the whole of this composite is biomodular. substrate is having some kind of modulus and this coating is having some other modulus. So when the component is under stress, it is more likely to that there is a debonding between the layer and the substrate.
Yeah,
So
delamination. Yeah. So as
debonding.
therefore, the composite film overall stress analysis is important. This is not only correlated with the semiconductor, but it is also like, for that matter, for bridges structure.
Yes.
There is the stress evaluation is being done by strain sensors. They put strain sensor, but overall the material which were being used for those hanging bridges, the type of stresses they were being studied.
Thank you. Thank you once again, sir, for sparing the valuable time, and it's a wonderful presentation you have given. Thank you, sir. So I now request Dr. Nirbhay Singh, co-convener of this workshop, to kindly present the workshop summary. Please, sir.
Thank you, sir.
Can
It is my,
Yes, sir. Rishi, sir. You can leave, sir. Thank you, sir.
Okay. Thank you.
Thank you, sir, for the nice talk.
Thank you.
So it is my privilege to present the summary of today's one-day national workshop on advanced characterization tools and technique for the material science and engineering. The workshop brought together eminent speakers, respected dignitaries, and enthusiastic participants from various academic and research institutes across the country. We begin with the joining of the participants, followed by the Saraswati Vandana and the formal felicitation of our distinguished guest by Professor P.K. Misra, sir, HOD Physics, provided a warm introduction to the workshop. The inaugural address by Professor Dr. R.S. Tomar, sir, Honorable Vice Chancellor, sir, and Lieutenant General V.K. Sarma, AVSM retired, Honorable Pro Chancellor, sir, offered a valuable insight into the importance of advanced characterization tool in cutting-edge material research. We also put a special thank to the Honorable Pro Vice Chancellor Research, sir, and our chief guest, Professor Dr. B.S. Rajput, delivered an inspiring address highlighting the rapid evaluation of the characterization technique and their role in strengthening scientific innovation. The technical session that followed were highly enriching. Session first delivered by Professor Jaisingh provided a detailed overview of electron microscopy. He discussed SEM, TEM, and HR-TEM technique, emphasizing their ability to reveal micro and nanoscale structural detail, defects, and elemental composition. His talk highlighted the role of modern electron microscopy in advanced material research. Session 2 by Dr. Muhammad Saeed Anwar focused on application of X-ray diffraction, XRD. He explained fundamental concept of diffraction, phase identification, crystallinity, and lattice analysis. He also discussed Rietveld refinement, that is a very essential tool for the confirmation, or you can say cross verification of the material structural analysis part. A modern synchrotron-based XRD, reinforcing the indispensable role of XRD in structural characterization. In session 3, which is presented by Dr. Dheeraj Singh, offered a valuable insight into Raman spectroscopy. He explained Raman scattering principle, its instrumentation part and its utility in identifying molecular vibration, bonding and structural changes, not only for general molecule, but also some virus-related study, or how this tool technique can be useful in biophysics, or you can say in field of biosciences. He outlined application in polymers, carbon material, semiconductor, and stress analysis, making the technique highly relevant for the diverse field. And in last, session 4, conducted by Dr. Rishi Sharma, who covered thin film characterization with a special focus on a film stress management, FSM. He explained the importance of analyzing stress in thin film and described techniques such as wafer curvature and laser-based measurement. His session provided an applied perspective linking thin film stress analysis to microelectronics, MEMS, and coating techniques. Each session offered substantial learning and generated meaningful discussion, greatly enriching the participants' understanding of state-of-art analytical technique. On behalf of Department of Applied Physics, I extend my heartfelt gratitude to all distinguished speakers for sharing their expertise, and to our Honorable Vice Chancellor, Honorable Pro Vice Chancellor, Honorable Vice Chancellor, Pro Vice Chancellor, Sir Research, for their constant guidance, and to all participants for their active and enthusiastic participation. We hope that today's workshop has broadened your knowledge and inspired new research direction in the field of material science and engineering, basically interdisciplinary area of sciences. And so thank you for contributing to the success of this event. Thank you so much. Thank you once again to all participants and our honorable administrative members.
Thank you, Nirbhay sir. Thank you for your summary. We are deeply honored to have with us Professor Dr. M.P. Kaushik, the Pro Vice Chancellor Research of the Amity University, Madhya Pradesh. Dr. Kaushik is distinguished scientist and administrator who served an illustrious career at the Defense Research and Development Establishment, Government of India, from where he superannuated as director and outstanding scientist in 2014. He has represented India on several international delegations to countries including the USA, Germany, France, the UK, and many others. In recognition of his exceptional contribution to the research and innovation, Dr. Kaushik has been conferred with numerous prestigious awards such as DRDO, Scientist of the Year Award, National Technology Award, and the Agni Award of the Self-Reliance. With over 181 research publications, 20 patents, and 9 technologies transferred to his credit, Dr. Kaushik continues to inspire academic research excellence at Amity University. His visionary leadership and mentorship has been instrumental in fostering a strong culture of innovation and inquiry among students and faculty alike. May I now invite Professor Dr. M.P. Kaushik, Honorable Pro Vice Chancellor Research of Amity University, Madhya Pradesh, to deliver the concluding remark of this workshop, initial workshop.
Thank you very much, Dr. Ashish. I hope I am audible to all of you.
Yes, sir, you are audible, sir. Clear, sir.
Yes, sir.
Dr. Mohammad Shahid Anwar of Senior Principal Scientist, CSIR Bhubaneswar, Dr. Dheeraj Singh, University of Delhi, and Dr. Rishi Sharma, a colleague of mine from Principal Scientist, CSIR Siri Plani, Dr. Pankaj Mishra, Dr. Vikas Thada, and all other faculty members and my dear students, those who are attending this international workshop, national workshop on advanced characterization tools and techniques for material science and engineering. At the outset, I'd like to thank or congratulate the organizers for organizing this particular workshop, which was very important and relevant in today's scenario. At the outset, I must tell you, the material development is in infancy stage in India. There are three things which needs to be addressed at the earliest possible, and I think the national mission is also on the development of new materials, new technologies, new devices. And new technologies, new devices will come only if the new materials will come into being. And when the new materials will come into being, their characterization by the different tools and techniques becoming a paramount importance. And hence, this national workshop is meeting all the requirement which is the need of the hour. As we come to closing moments of this national workshop, it gives me immense satisfaction to reflect on the depth and quality and relevance of the discussion we have witnessed today. In the beginning, I would like to tell you that since morning, we have been discussing about the different techniques. So there are two types of techniques which have been discussed, that is microscopic as well as spectroscopic. As far as microscopic is concerned, we are discussing SEM, TEM, and other the atomic force microscopy. And at the same time, on the other side, when we're talking about the spectroscopic techniques, we're talking XRD, then other IR, NMR, UV, all spectroscopic techniques are discussing. And these are all a very important aspect of it. At the beginning, I must tell you that what is the general impression I got it after hearing so many experts, that everybody was talking and everybody gave an excellent talk, and then a complete overview was given about the characterization tools and techniques which are being used for the characterization of the materials or development of materials or development of devices. But the general impression which I was getting is that everybody is thinking that the new material is going to be solid alone. Because when we are talking about SEM, they are talking about the surface phenomena, the surface characteristics which SEM will describe. Similarly, when we are talking about TEM, then it is understood that okay, internal structures will be discussed or will be characterized or will be evaluated with the help of a TEM. But every time the type of nature of the material which we are going to characterize was in general, I think by and large, everybody was considering as a solid. Fine. As far as solid materials are concerned, you can go ahead whatever the way it has been discussed. But what about materials? Liquid materials. The materials can be solid, materials can be liquid, material can be semi-solid or semi-liquid. All these things can be there. So when we have to characterize, which is either in the pure form or slightly impure, so impure has to be purified. And then if the nature of the sample or the nature of a material is liquid, then some of the talk in the beginning have no doubt it can be done with the SAM, it can be done with the TEM, but I think some modification or some attachment, new modification attachment need to be described or has to be done. Because for example, liquid has to be converted into solid, it has to be in the crystalline form, it has to be in amorphous form. So for that, cryo EM, that is cryo electron microscopy, is being used, or for the liquid cell, electron microscopy is also being used. They are basically the main equipment, but these are the further attachment is there. And solid as well as liquid sample can also be done by microscopic as well as by the spectroscopic technique like XRD, which I'm mentioning over here. Now in XRD, what has happened is, XRD normally we go it for the crystal structural determination. Mostly, no doubt it can be amorphous. Also, the structure is also being done by the XRD. But mostly, if at all we want to look for the new structure, or if we want to go into the structural feature of a material, then we have to go for crystallization. And if the liquid sample is there, the liquid cannot be crystallized, so it has to go. So it has to be cryo. So it means these liquid sample need to be crystallized at a low temperature, and that too under liquid nitrogen. The attachment in the XRD is made in such a way so that the temperature goes up to minus 270 degrees centigrade, and then slowly the crystallization of the liquid sample takes place, and ultimately crystal structure of a liquid sample is being determined. So these are some of the other concerns which I thought of bringing to the understanding of all these scholars, research scholars, the faculty members, those who are attending. So it means the techniques, characterization technique, whether it's microscopic or whether it's spectroscopic, they all liquid and any kind of material can be done. This is what the Professor Jessing was also talking, the biological material. So biological material has to go as such. For example, if I want to take serum, if I want to take plasma, if I want to take blood samples, similarly other water bodies, water from these has to be taken. For example, in case of pharmacokinetic studies where we do the kinetics of the drug which normally we take, so whether how the distribution is taking place, how the excretion is taking place, how the absorption is taking place. So it means if at all we have to monitor whether the kind of drug which has gone in our body system, what is the state of affairs, whether it has degraded or we are getting the degraded product, or simply the drug is getting excluded from the body side. So that can also be monitored. So it means the sample is being taken, they're directly being subjected to either microscopic techniques or spectroscopic techniques. So it means all these things is very important. So throughout this workshop, what I have learned is that we have explored a wide spectrum of advanced characterization techniques, as I mentioned, the electron microscope, X-ray diffraction, Raman, FTIR, thermal and mechanical analysis to modern surface and interface characterization techniques have been described in detail. Actually, these tools, these spectroscopic techniques are no longer just a supporting instruments in the material research, but they have become very important foundation upon scientific progress in build, because until we do not characterize, we will not able to do anything. So characterization of any materials, or particularly whenever we are converting to device technologies, it has become all the more important. And some of the things which we cannot visualize with the naked eye, we have to depend on otherwise immeasurable, immeasurable and understand materials at the atomic and molecular level, so that we know that how they are going to react, how they are going to interact with other material by subjecting to reaction. If at all we have to do the reactions of two molecules or two chemicals or two materials, if we have to fuse. Like other day, last workshop or international conference where we were discussing, if at all some polymeric materials are there. So it means we have to go by additive manufacturing. So additive manufacturing, before additive manufacturing, whatever whether it's a polymer, whether it's a material, whether it's a metal surface or aluminum or iron or steel, we have to characterize and then see to it the compatibility with the other parts where we are going to do the additive manufacturing. So it means that has become all the more important. Any kind of manufacturing we go, or any kind of devices development we go, we have to have the characterization of the material which we are going to make use of it. So our deliberation today have resulted in several important outcomes. First, participant gained throughout thorough understanding of how advanced characterization technique tools can be strategically used to establish structural property relationship. That is very important, because structures, we know what kind of properties we are going to expect by combining two materials. Then only we'll able to do something, and that becomes an essential requirement for designing new materials and optimizing existing ones. So this clarity on the capabilities, limitation, and correct selection of the characterization instrument will empower researchers to plan experiment more effectively. Interpretation of data will become more easily, and it will be more accurate and strengthen the scientific rigor of their investigation. Second important aspect which we have achieved through this conference workshop which I was attending in the morning sessions, the workshop has encouraged a broader perspective on interdisciplinary collaboration, which is very much looked at. It is not the domain of physics alone. The physics, chemistry, biology, this which the Professor Jessing as well as Professor Dheeraj was discussing. It means any kind of material need to be developed, need to be characterized. So it means it has to become interdisciplinary in nature. And many of you express interest in integrating characterization techniques with computational modeling, nanotechnology, semiconductors, device fabrication, semiconductor. In the morning, the chief guest, Professor Rajput, was mentioning, and he highlighted that what is the role of quantum dot, quantum wire, quantum planes, buckyballs, and quantum mechanics, how it has played an important role in developing the new materials. So this cross-pollination of ideas is a significant outcome in itself, and it opens new pathways for joint project, collaborative publications, proposed writing, and utilization of shared research facilities. So the discussion today have laid a strong foundation for long-term academic partnership and innovation drive research. So what I will say that finally I'll say I'm very delighted to see the enthusiastic participation which was there since morning from faculty members, doctoral researchers, young researchers, that across India. It's not only from academic institutions in and around Gwalior, but some of the students from NITs, IITs, and central universities and other universities have participated in a very big way. So your curiosity, questions, and engagement throughout the session reflect a vibrant academic culture that values innovation, rigorous inquiry, and continuous learning. I firmly believe, because I have been associated with this type of activities or being in science domain for a last 40 years. So I firmly believe that the ideas and knowledge shared today will translate into stronger research proposal, high quality publications, innovative experiments, and meaningful collaboration within and beyond our institutions. I take this opportunity to congratulate the department head, Professor Pankaj Mishra, and all his colleagues and the entire organizing team for their meticulous planning and tireless efforts. Your commitment from designing the technical programs to coordinating resource person and ensuring smooth execution has made this workshop a resounding success. My sincere appreciation to all of you also goes to the invited speakers from B.S. Rajput to that of Professor Jaising, then Professor Mahmood Anwar, then Dr. Dheeraj Singh and Dr. Rishi Sharma. And my goes to all of them who has taken their valuable time and greatly elevated the academic value of this event. As we conclude, let us carry the momentum of today's learning into our ongoing and future research endeavors. Let us work together to strengthen our university contribution to the material science and engineering, and to position ourselves as a hub of innovation, excellence, and interdisciplinary research. Thank you all once again for your active participation, insightful discussion, and constructive encouragement. I wish each one of you great success in your academic and research pursuit. Thank you very much. Jai Hind.
Jai Hind, sir.
Thank you so much, sir.
Thank you, sir. We appreciate your time and sincerely thank you, sir, for your meticulous and enlightening concluding remarks. May I now request Dr. Nasir Khan, sir, to deliver the vote of thanks.
Thank you, sir. I'm audible, sir?
Yes, sir, you are audible, sir. And with the
distinguished guests of the day, Professor Dr. B.S. Rajput, ex-Vice Chancellor, Kumaon University, Nainital, Uttarakhand, Dr. Jaising, Professor Physics, Guru Ghasidas, Central University, Bilaspur, Dr. Mohammad Sahid Anwar, Senior Principal Scientist, CSIR, Bhubaneswar, Dr. Dheeraj Singh, University of Delhi, Dr. Rishi Sharma, Principal Scientist, CSIR, Honorable Pro Chancellor, Lieutenant General V.K. Sharma, sir, ABSM retired, Honorable Vice Chancellor, Professor Dr. R.S. Tomar, Vice Chancellor, Research, Professor Dr. M.P. Kaushik, Registrar, HOI, HODs, faculty members, and participants. National Workshop on Advanced Characterization Tools and Techniques for Materials Science and Engineering is towards its successful culmination. And I, Dr. Nasir Khan, deem it a great honor and privilege to propose a formal vote of thanks on this occasion. We are thankful to Professor Dr. V.S. Rajput, sir, Professor Dr. Jai Singh, Dr. Mohammad Sahid Anwar, Dr. Dheeraj Singh, Dr. Rishi Sharma to spare their valuable time and enlightening us with their pulse of wisdom. Sir, we are indeed thankful to you all. At the outset, I would like to register my sincere and humble thanks to Honorable Pro Chancellor, General V.K. Sharma, sir, for his motivation and guidance. He had been a great source of inspiration throughout the workshop. Thank you, sir. Profound thanks and gratitudes are due towards Honorable Vice Chancellor, Professor Dr. R.S. Tomar, for his continuous encouragement and connecting us to the best speakers of the globe. We are indeed extremely fortunate to listen to them. Thank you, sir. Profound thanks and gratitudes are due towards Honorable Pro Vice Chancellor Research, Professor Dr. M.P. Kaushik, sir, for his continuous encouragement, advice, and valuable suggestion. Thank you very much, sir. I would like to congratulate and appreciate the committee members of this national workshop for putting in their heart and soul to make this workshop happen successfully. I would like to take this opportunity to extend my thanks to IT department for their support. I also wish to thank the faculty members and participants who have contributed in this conference with such a zeal and enthusiasm. I wish you all the best for your bright future. Last but not the least, I would like to thank all the students of Amity School of Engineering and Technology for being an enthusiastic and wonderful audience. Once again, I thank you all. Jai Hind, Jai Bharat.
Thank you, Nawaz, sir. As we conclude this workshop, I extend our sincere thanks to all dignitaries, speakers, participants, and the organizing team for making it a grand success. The session may have ended, but the ideas and collaboration will continue to grow. Wishing you all the very best, and we look forward to meet again. Thank you all. Have a good day ahead. Thank you, sir.
Thank you very much to all of you. IT host, kindly close the meeting.